by 3. So here you can see that from 5 by 5 to 3 by 3 size reduction happened. That means the width and height of the image is reduced. So we can find out how we go for the output dimension. So output dimension is nothing but the input dimension minus kernel dimension plus 2 padding by stride plus 1. So here stride means the movement of the mask. Here moving by one. So the stride is 1. Padding means if you want to have the same size of the image, you have to use 0 padding. So here we are not using any padding. So padding becomes 0. So then the output dimension become input size is 5 minus 3 plus 2 into 0, padding into 0 by 1 plus 1. That is 5 minus 3, 2, 2 by 1, 2, 2 plus 1, 3. So here you can see that the output size is 3 by 3. Okay, so this is how we do the convolution. So after convolution, and similarly when you do the convolution, you can define a set of filters. Say for example, you are selecting one filter, it will give only one result. If you select n number of filters, it will give n number of results. So here you assume I am taking 4 number of filter or kernels with a 3 by 3 for the previous case. So I am getting 4 such feature maps. Okay. So let me tell you, I have a width of 5 by 5 for the input image. I'm doing a convolution with the 3 by 3 kernel size. Okay, kernel size 3 by 3. I'm getting a size as we seen earlier 3 by 3, right? So my width and height is reduced to 3 by 3. Now I have assume that I have 16 number of such filters. That means my depth will be 16. So I am reducing my width and height to 5 by 5 to 3 by 3, and I'm increasing the depth. So if you do the convolution again by 3 by 3, so it is become 1 by 16. So that means your width and height is now reduced and you are getting a depth information. So in this figure, you can see that width and height are reducing and depth is increasing. So finally, you will get a depth information regarding the input image. So that is the idea of convolution layer. So in deep neural network or normal perceptron, we have seen after the summing operation, we are applying a nonlinear activation function to activate, right? Same case here also, after the convolution operation, we have to activate the layers using an activation function, and here we are using ReLU, that is rectified linear unit, or ELU or leaky ReLU for the applications. So generally we go with the ReLU, and the activation layer accepts input volume of same size and it is providing the output volume of same size. So let us see an example. So this is the convolved image. Assume that this is the convolved image or the convolution output, and here you can see that I am going to apply a ReLU activation function. So you can see that the size of the image is 4 by 4, and after applying ReLU will give only values for the positive numbers. So all negative values will be 0. So here two negative values are say -8 and -6. So these values become 0 over here. So we have done the activation and all other values are same because all are positive. So here there is no dimensional change. So our convolution operation is over. Next, activation is over. Now we are going for pooling. Why we go for pooling is that we are generally using a large image size, right? So such a more number of images are there. So we need to process these images as a whole at a time. So it will be quite difficult to process this much information in a single stretch. So we need to reduce the receptive field size of the image. So what we do is, initially we will take an input image, we will do convolution, activate using ReLU. After that we will pool. So there are two set of poolings are available, max pooling and average pooling. So let me explain this max pooling. So here I am having the previous activated 4 by 4 image size. So here I am going to select a pool size of 2 by 2. 2 by 2 means a 2 by 2 matrix, and with a stride of 2. Stride of 2 means I am moving this matrix by 2 levels. So first I can consider the first 2 by 2 values over here. So in max pooling, I need to find the maximum value of the pixel. Maximum value of the pixel, that means 3. Then I am moving to the right 2 corner. So this is the maximum value is 12. Then I am moving to this one by 2 more factor. So the maximum value is 6. Now I am moving to this maximum value is 3. So this is known as max pooling. And here you can see that the size is reduced to 2 by 2 after pooling. So the output dimension is input dimension minus kernel dimension by stride plus 1. So here the stride is 2, padding is not applicable here. So what is the input size for output size? Sorry, kernel dimension 2 by stride 2 plus 1. So 4 minus 2, 2, 2 by 2, 1, 1 plus 1, 2. That means your image is having a size 4 by 4, that is again reduced to 2 by 2. So the receptive field size, that is width and height, is again reduced to from 4 by 4 to 2 by 2. So this is the case with max pooling. And if in case of average pooling, instead of taking maximum value, we will consider this matrix and we will take the average of that. We'll put it over here. Similarly, we will consider this and take the average. For this one also we'll take the average. This one also will take the average. Okay, this is the difference between max pooling and average pooling. So by using average pooling or max pooling also, we are reducing the receptive field size. So we can reduce the dimension of the image. So that will reduce the total receptive field of the image. So next is fully connected. So after the convolution operation, we need to classify, right? Classify or go for regression. So for that, we need to use fully connected networks. So the methodology is like this: input, convolution neural network, ReLU, pooling. Again, if you want to convolution, ReLU, pooling. After that, two fully connected networks. So the maximum two fully connected networks you can give here. So this fully connected network will be given before the final classification layer. Totally, you can give 3 fully connected network, and the final fully connected network should be the classification layer. Next is batch normalization. So batch normalization layers, as the name suggests, are used to normalize the activation function. So as you've seen in the previous slide for the activation functions, all the values are there, right? So large values. If you want to normalize that to in the range of 1 to 0, if you want to reduce the computational complexity, you can normalize it using the maximum value. So here the batch normalization is, we are normalizing the value before pooling. So between convolution and ReLU. So you have to input the data, do the convolution. After convolution, you batch normalize, then you go for ReLU, then pooling. So this is the new strategy now. So next is dropout. So when you consider a fully connected network, as I said earlier, since the name suggests fully connected, that means all connections, all nodes have connection to other nodes. So this means there is no dropout, and a dropout means of 50% means, let's say for example, here you have 12 connections and all are connected together, and a dropout of 50 means it will take only 6 connections, and that connections will be very useful connections only. And it is removing balance 6 redundant or unwanted connections, and that is not contributing towards decision making. So we can simply use this dropout to avoid redundant data path. So because of that, we can reduce the overfitting and we can go for better representation. So it will give you a better result compared to this one, and it will reduce the overfitting. So now we have to design our network like this: convolution, batch normalization, ReLU, pooling, fully connected, dropout, fully connected, dropout. This is the final classification layer. So this should be the process flow we have to follow. So now we have to see some common architectures and training patterns. So the general architecture is like this: input, convolution, batch normalization, ReLU, that is n times. That means maximum 3 times. So when you design a convolution neural network by your own, you have to give maximum 3 convolution, batch normalization, ReLU together. That is the condition. And including convolution, batch normalization, ReLU, pooling, you can give m times, more than 0 times. That means it may be 4, 5, 6, etc. And fully connected and ReLU should be maximum 2 before the classification. So 2 fully connected should be given before the classification layer. That will be the maximum. So if you know this rule, you can easily design your own customized networks for your application. The next is cost function. So we have seen the loss function or cost function earlier in case of the forward and backward propagation. So the cost function is nothing but half of y minus y cap, where y is the original output and y bar is the predicted output. So our main aim of the network training is to reduce the cost function or minimize the cost function. So there are 2 cases for the cost function. The first one is minimization and second one is maximization. In minimization, the returned value is usually called a cost, loss, or error. So if the error is coming, we need to reduce it or we need to minimize. The goal is to find the values of the model parameters for which the cost function returns a small value as possible, so that we can get a better prediction of the input. In maximization case means when we consider as this as an reward. This is in case with a reinforcement learning. In reinforcement learning, we consider the outcome as a reward. So in that time, we have to maximize the cost function. But in all other supervised or unsupervised case, like we have to go with minimization of the cost function. So now we are moving to hyperparameters. I think you heard about some hyperparameters. Hyperparameters tuning. So when you tune hyperparameter, then only you will get a better results. So the hyperparameters are the parameters whose value is set before learning process begins. So we will set the learning rate, number of epochs, hidden layers, hidden units, activation functions, etc. These are some of the examples for hyperparameters. And why we go for this hyperparameter? Because choosing a good hyperparameter provides two main benefits. First one is efficient search across the space of possible hyperparameters and easier management of large set of experiments for tuning. And there are two set of hyperparameters. The first one is optimizer hyperparameter and second one is model hyperparameter. So these are the two set of parameters we need to tune. And when we come to the optimization hyperparameter, the first one is the learning rate. So learning rate means if the model learning rate is too small than optimal value, it will take much longer time to converge. And if it is very fast, it will fastly converge. You won't get the exact solution. So a reasonable learning rate is generally we use with the 0.001, and we have to see the different selection of learning rate. If you consider the first figure, you can see that validation error decreases during training. So error is decreased during training, and that is optimal in nature, and it is reaching the minimum. So you can see that it is a good one. Similarly, here also validation error is decreasing. So here you can see that this is the error. It is coming here, it is coming here, it is coming here, and finally it will reach here. So it is also a good learning curve. But when you see the validation error decreasing too slowly, it is coming very slowly. So it will take large time to converge because its learning rate is very small. And similarly here also, in the first case learning rate is here, second it is increasing, again it is increasing, the error is increasing. So that means your network is not good. So by looking at the loss curve itself, you are able to identify whether your learning rate is good or bad. So based on that, you can adjust your learning rate. So other optimization parameters are batch size. So the total number of training examples present in a single batch. So generally we split the entire data into different batch sizes. Let's say for example, it may start from 1 to 256. So but a fair value of mini batch size is 32. This is obtained by empirical experimentation. And when you design a network, you can use a batch size of 32. That will be giving some better result compared to the other batches. And epochs means one epoch is when an entire data set is passed forward and backward through the entire neural network only once. Let's say for example, consider that you have 2000 image samples or data samples. When you pass the 2000 sample forward and backward through a network, that is known as one epoch. Okay. So now the iteration. So iterations is the number of batches needed to complete one epoch. So the number of batches is equal to the number of iterations for one epoch. So in better way, I will explain with an example. Let's say we have 2000 training examples that are going to be used. So divide the 2000 samples into batches of 500. So, that means 500 is the batch size. Such 4 batches are there. So you are getting 2000. That means 500 is the batch size. You have 4 number of iteration, which completes one epoch. So in the batch size of 500, out of 2000 data, you have 4 iterations to complete one epoch. Okay, so this is the idea. So I think you got it. Dividing the data into batches, the batches into number of iterations will give you the epoch. So this is the relation between batches, iteration, and epoch. Then model hyperparameter. So there are more involved in the structure of the model. Previously, we seen about the optimization parameters, right? But here it is comes with the model hyperparameter. So this is talking about the number of hidden units. Number of hidden units is the main measure of model's learning capacity. So number of hidden units we need to decide. Slightly more number of units than optimal is not a problem, but much larger number will lead to overfitting. So we cannot simply put more number of hidden units. We need to fix the minimum by using trial and error methodology. The number of layers. So it is often the case that a 3-layer neural network will outperform 2-layer one, but going even deeper rarely help much. So for example, I am going for a classification task with the 2-layer one. I'm not getting the result as I expected. I'm going for a 3-layer, I'm getting good result. But that doesn't mean that if I go for 4-layer or 5-layer, it will give much better result. So that is the case. So we need to fix the number of layers by using experimentation. So next is overfitting. So when the model learns details and noise in the training data to degree that it is adversely impact the execution of the model on new information. So here simple example is the training accuracy is high and validation accuracy is low. That is the problem with the overfitting. The training accuracy is better. That means the good memorization ability, but bad generalization ability because validation accuracy is low. I will tell you an example. So here a model is looking at the cars and trucks, but only recognizes trucks that have a specific box shape. It might not be able to notice a flatbed truck because there is only a picture, a particular kind of truck it is showing in training. So the model performs well on training data, but not on the real world. So I'm taking a few set of data of a car and a trucks, and I'm training only with a specific box shaped truck. Okay, but I am testing. When I am testing, I am giving a flatbed truck. I'm not getting the result because during the training that model doesn't saw any flatbed truck. So that means the training accuracy will be high because it is training with available data. But when validation, I am validating with another kind of image. So this will lead to overfitting. So how can we avoid overfitting? So that is one thing is we need to get more data for training and choose correct epochs by early stopping and cross validation and dropout. So dropout we have already seen. Cross validation means, let's say for example, you have 1,000 data of one category and another category of 100 data. So there is a huge data imbalance. So whenever we go for a neural network design, first you have to see the number of images in the each category should be at least equal in nature. Otherwise, there will be a data imbalance. So here you can see that the class A is having 1,000 data and the class B is having 100 data. So there is a class imbalance. In such cases, we have to go for cross validation. In cross validation, generally we go for tenfold cross validation. In tenfold cross validation, what we do is we will divide the entire data set into tenfold. That is, this 1,100 data set will be divided into tenfold with 110, 110 on each. Then we will take 9 out of 10, 9 data set will be taken for training and 1 will be taken for testing. Okay. So after this process, we will put it back to the 10th group and we will take, this will be put it back, the tested will be put it back, take another one for testing. So similarly, we have to do this kind of activity for the entire 10 blocks. Then you have to take the average. So that will give you a tenfold cross validation. So this is better when we go with the huge data imbalance or you have a less number of data. And dropout we already seen, and choose correct epochs by early stopping. So when you go for a neural network training, so you can set the epochs by early stopping. That means you can have a patience. Patience means you are setting the patience level. That means when you have this accuracy curve, training curve, you are getting this accuracy like this. You can see that after reaching here, okay, at this epoch, let's say for example 50 epochs, you are having this accuracy, let's say for example 90. After that it is same for all the values, right? So what I'm going to do is I'm going to put a patience of 10, patience of 10 in the early stopping criteria. That means after reaching 50, I'm getting 90%, right? So again, this will go for 10 more iteration. That means 60 or approx 60s. So that is from 50 you have 10 patients. So after reaching 60, I am getting the same accuracy means if I am going again beyond this, it won't give a better result. So that means my data is going to overfit. So what I will do is, so I am getting here 10 epochs as my patients. So I'm getting 90% at the 60 epochs itself. So there is no change from 50 to 60. So my network will stop working at this 50 epoch. So 50 epoch will be the value you are getting as a result. So after that, the network is going to overfit. So this is the early stopping idea. So using early stopping, we can stop the process, training process. Otherwise, it is unwantedly do the training process. So you can use early stopping. Second is underfitting. So a model that is neither well trained or data or nor can generalize new information. In overfitting, we can see that training accuracy will be good, but validation accuracy is low. But here in underfitting, training and validation accuracy both are poor. So usually it happens when model is too small. The condition or the scenario when we are getting this kind of result is either the model is too small or you may have less amount of data. Okay. So this underfitting has both poor performance and accuracy, and solution is to add more networks to the layer. Sorry, add more layers to the network. Choose correct epochs by using early stopping. Similarly, cross validation. If you have less amount of data, you can go with the cross validation. And if you have equal number of data, say for example, a batch A having 10,000, batch B also having 10,000 data, that means you are having equal number of data. That time you can go for 80% of data for training, 10% of data for validation, 10% of data for testing. So you can do like this if you have equal number of data samples. And now we will see a set of pre-trained neural networks. Pre-trained neural network means the neural networks which are developed by Google or Microsoft and or other research people, and those are trained on ImageNet dataset. So ImageNet dataset is a general dataset which contain the natural images. Okay, so it doesn't contain medical image. So we cannot directly use the pre-trained networks into medical imaging application. And these are the networks. And the problem with these networks are it is having huge number of learnable parameters, and the size of the networks are high, and also it having large depth. And these are the learnable parameters of different networks. Next is transfer learning. So transfer learning is a methodology which is used in deep learning. So when you consider the traditional machine learning, we will take one set of data set, we will learn the system, and we will test with another data, and we will get the result. If you have another data set, we have to learn it using the same machine with the same data set. Then only it will learn, because the machine need to know what is the data. In the machine learning, generally we can say that the model is an exact replica of the content in the data, so that it can identify very easily. But in transfer learning, we are training with one set of data and testing with another set of data. That means, let's see, for example, all the pre-trained networks like ResNet, GoogleNet, AlexNet, all of them are trained on ImageNet. Okay, ImageNet. So this may contain bus image, car image, Jeep image, scooter image, bike image, everything, tree image, animal image, everything. Okay, so these networks are trained on ImageNet, and it is having a weight and bias. Okay, so we can transfer this weight and bias. That is what the term called knowledge, or transferring the learning. Transfer learning means transferring the learning done by one network. That means, let's say for example, I'm taking ResNet. This ResNet is trained with the ImageNet data, and after training we will get the pre-trained weights and bias. I'm taking this weight and bias, and I am collecting a set of images of car, bus, and truck. Okay, I am collecting by my own, and that data set will be the second data set. I can test that data set directly with ResNet without doing any training. So this is one kind of transfer learning, that is transferring the learned knowledge of one data set to another. So this is applicable only with the general images. This is not applicable with the medical images because the image data set doesn't contain medical images. So it is not seen any medical image during training. So it cannot classify the images, medical images. So that's why we are going for another transfer learning. This is known as fine tuning. Fine tuning. Fine tuning means we will take a pre-trained network. Say for example, I am taking a ResNet. I am going to freeze all the common layers. All the common configuration layers I am going to freeze. So for that, I am using the same weight and bias which is run on the ImageNet. After that, what I am going to do is I am going to add a few more fully connected layers as custom layers by my own. I am adding a few layers by my own. Then I am going to train the entire network with the medical imaging data. Okay. So when I am training this layer with the medical imaging data, up to this, it will take the weight and bias of the ResNet, which is trained on ImageNet. After that, it will train with the medical image. Now, my network is trained with the medical image. Now we can use medical image to test the network. So this is known as transfer learning with the fine tuning. So for medical imaging kind of application, we have to use transfer learning with the fine tuning. So next is generative adversarial network or GANs. So GANs are generally used to develop synthetic data. If you want to get more data, say for example, you are having 100 data of a particular disease and you have 1,000 data of normal. So there is a data imbalance. So you can increase the number of 100 to 1,000 by means of GANs, that is generative adversarial network. So we will see how GANs generate the images. So here you can see that there is an actual sample and there is a generator. So the input to the generator is a latent random variable, and the generator generates an image initially from the noise, and that will be sent to the discriminator. So the discriminator will compare it with the original, and the difference will be taken as the loss, and that will be given to the generator. So generator will redefine the image again and it will pass, and this process repeat until the produced sample is equal to the original sample. So this is how we are generating synthetic data. So GAN is very useful in generating synthetic data for medical image processing. So these are some of the applications for generative adversarial neural networks: the data augmentation, face frontal view generation, generate examples of image database, generate photographs of human faces, generate realistic photographs, generate cartoon characters, image to image translation, text to image translation, semantic image to photo translation, generate new human poses, photos to emojis, photograph editing, face aging. I think you are aware about face aging app, photo blending, super resolution, photo implanting, clothing translation, video prediction, 3D object generation, etc. So these are some of the applications. Let me show you some sample examples. This is a style GAN. So from this image, generating realistic faces. From this image only it is generated. So from one person's image, we can generate other person's face. So this is on a style GAN. And next is cycle GAN. Using cycle GAN, we can generate another kind of image from one kind of image. So here we are having a horse. From the horse image, we are generating a zebra. So from zebra, horse to zebra, then zebra to horse. So this is also possible with the cycle GAN. Then big GAN. Big GAN is used to generate high quality, high resolution images. Increase the resolution of the images. Then pix to pix, paired image to image translation. That is input labels to street scene. That is aerial to map. Labels to facade. Black and white to color. Day to night. Edges to photo. These all are possible with these GANs. So next, the cycle GAN is used for image augmentation. So as I told earlier, if you have less number of images for a process, say for example, I'm having 10,000 images of normal and 1,000 data for abnormal. Say for example, some liver cancer. So when I'm doing this operation, there is a huge data imbalance. So what can I do is I can use cycle GAN for generating synthetic data using cycle GAN. So here you can see that these are the true contrast CT image generated from the device, and this is the synthetic non-contrast CT obtained from the same image. Similarly, true contrast and synthetic non-contrast. And this is a true non-contrast CT images. You can see that we can generate these images from original. Okay, so we can use it for augmenting the data. And here you can see another example. This is a normal chest X-ray, and this is the COVID-19 X-ray we have developed in our lab using cycle CAN. So you can see that the COVID patients are here. So we generated from a normal to COVID. Similarly, you can from COVID to normal. So that is also possible using cycle GAN. So here you can see that the synthetic liver lesions generated for the work. So you may have doubt whether we go with cycle GAN, it will give a better result or not. So let's see with an example. Here there is a publication in IEEE Transnational Biomedical Engineering in 2017. This is from a team of Israel. They have done some research on this. So they look for liver lesion classification using GAN. So they have considered cyst metastasis, the cancer, and the hemangiomas, that is benign cancer tumor. So initially they have done with bag of visual weights with machine learning. So that time they are getting the average weighted result of 78% sensitivity and specificity of 88%. Then what they done is simple CNN augmentation they have done. That means they have simply rotated the image, shear the image, translate the image, and doing lot of geometrical operation. They have augmented the data and they have tried the result. You can see here the result is just improved by 0.6 and here improved by 0.1. But when they do the operation with CNN augmentation, that is GAN operation, CNN with the GAN, you can see here the specificity is increased from 88 to 92.4. Similarly, the sensitivity is increased from 78 to 85.7. So this indicates that the GAN can be used to generate synthetic data for medical image processing. So this is one of the example. And second thing, we can generate one kind of modality image from another modality. Say for example, you can see the PET, positron emission tomography, and computer tomography. So generally, it is important or standard diagnosis for standing in oncology and supports detection of localization of malignant tumor and evaluation of tool for new drug therapy. But PET is not always available, and it is radioactive and it is expensive, still not offered in all of the medical centers. So PET is very costly and it is radioactive. We are injecting some radioactive material to the patient. So after taking the PET, the fellow need to be isolated for 24 hours. So because of these reasons, PET is not used. So researchers were thought, is it possible to generate a PET image from a CT scan? So that developed virtual PET, that is generating PET from CT or from CT to PET. So here what they do is they will take a source CT image and using a trained fully convolutional neural network. From that, they are getting the learned feature. Using that, they use a conditional GAN. And using that conditional GAN, they have generated a PET-like image. So here you can see that this is the PET-like image they have generated from a CT. So here you can see that this is the CT images and this is the PET CT images. PET image, and this is the PET image obtained using that conversion. That means PET, CT to PET. You can compare with these two. This is the original one. This is the generated one. This is also the original one, generated one, original one, generated one. There is no much difference. So using this, you can go for generation of PET from CT. That means you can develop data of one modality using another modality. So next is use of virtual PET in disease diagnosis. So initially, what they done is they have taken the CT using a detection software. They detected the disease, but actually the detection software would give a FPR of, that is false positive rate of 2.9 and true positive rate of 95. And here you can see that there are a few more points are not the disease, but that is identified in the CT. So what we generated is we generated a PET using the CT. After that generation of PET, we compared with the PET result, so that you can see here Here, how many lesions are there? 1, 2, 3, 4, 5, 6, 7, 8 lesions are there. Okay. But actually, how many lesions are there? 1, 2, 3, 4, 5. 5 lesions are there. Actually, the disease lesions are only 5. But when you go with only CT, you are getting 8. That is a misclassification. But when you go with a virtual PT for another comparison, it is giving only 5 correctly identified lesions. So that you can see here the false positive rates are reduced to 2.9 from 2.1. That means a 28% of false positives are decreases. So this work is done by Avi Ben Cohen from, I think, Israel. It is published in 2018. So they have developed this work. So they already proved that the GANs can be used for generating synthetic data, and secondly, we can generate virtual data from one modality. The next is the ways of addressing challenges in medical images. So challenges in medical images on the one side and the solutions for overcoming challenges. So if you have less number of training sample, you can go with the augmentation. If you sparsity of labeled data, you can go for semi-supervised learning. And noises in the image, you have to filter it using Gaussian filter. And thicker CT images of the brain, you have to go for geometric normalization. Exact local and global feature, you have to go for multipath CNN, more paths in the CNN network. Reduce classification error, train on misclassified image batches. So avoid redundant computation, ROI segmentation using FCNN, that is fully convolutional neural network. Herd classification, 2-pass CNN. Why 2-pass CNN means one for spatial and another for temporal features. Next is imbalanced data level distribution, two-phase training. Less resolution in brain images, slice by slice segmentation. Increase the accuracy by AUC in eye images, ensemble learning, that is boosting instead of backpropagation. And efficient CNN architecture for medical images. For brain MRI, for Alzheimer segmentation, you can go with the LeNet or GoogleNet. For detection, you can go with multipath CNN. Epilepsy, you can go with the classification with CNN with the 7 convolution neural network. Schizophrenic or bipolar disorder, that is dementia kind of disease segmentation, you can go with the patch-based CNN with the 4 convolution, 2 max pooling and softmax regression. For tumor segmentation, you can go with convolution max pooling of maximum 2 with the 2 fully connection. Detection, we can go for scaled PGG or GoogleNet with the transfer learning. For classification, you can go with AlexNet with the transfer learning. Localization, you can go with semi-supervised deep CNN. For segmentation of HAD CT, you can go with the 2-pass CNN. For HAD ECG classification, 2-pass CNN, one along spatial and another along temporal. Then finally, we have to fuse together. Then HAD MRI for left ventricle localization, we can go for convolution with the 2 number of convolution filters. So next for lung CT, for cancer classification, ensemble of OR feet across axial, sagittal and coronal plane. So 3 locations are there. 3 planes are there, axial, sagittal, coronal. So these 3 we have to consider. Then for nodule detection, you can go with the LeNet or OR feet. COVID-19 classification, you can go with the multi-scale or multi-encoder ensemble CNN model. In ILD classification, any CNN network like AlexNet. And classification, for general classification of Hep2 cell, you can go with a convolution with 3 convolution layer and 2 fully connected and softmax layer. Then for eye hemorrhage detection, you can go with the 5 convolution neural network. And for glaucoma, you can go with the 2 convolutional with the fully connected with AdaBoost or any other classification. And next is the retinopathy. In retinopathy, we can go with the 10 number of layers of convolution and 3 fully connected with the softmax layer. So these are the examples. And for colon, we have polyps, polyp classification, any simple CNN architecture. For detection, ensemble of CNN, that is a combination of 1 or more CNN networks. Then skin melanoma, you can go with the 2 fully connected, full convolution neural network with the fully connection. For liver CT classification, maximum of 2 to 3 convolution neural network with the 3 fully connected and softmax. And abdomen ultrasound scan, we can go with the 2 or more convolution layers and with a fully connected. So now we are going to do some experiments which we have done in our lab. So first one is the object detection. So generally when we go with object detection for deep CNN, so in that case we try to detect the object in an image So here you can see that there is a deer in the image. We want to detect that deer and we have to specify what object it is. Okay, so for that we are using object detection algorithm. In this object detection algorithm, will give you the score, that means the probability of that object, and the box coordinate, and it is representing its name. So there are object detections are two types, the one-stage detector and two-stage detector. In one-stage detector, we have single shot detector SSD or YOLO, that is you only look once. And in two-stage detector, we have region-based CNN, that is RCNN, and fast RCNN. So in two-stage detector, there are two stages will be there. First stage, there is a sparse set of proposals are generated. And the second stage, the feature vectors generated in the proposals are encoded by deep convolutional neural network, and it is identifying each object in the class. So it is very providing very good result, but it is taking some time because it have two levels. So one example is the object detection using RCNN. It generates actually two outputs, K class probabilities and for object boundaries. So here you can see that object detection. Here in this picture you can see there are a few number of cows. So you can see that each cow is detected and it is marked with a bounding box with the name cow. Okay. So this is the result for this object detection. And when we come to the one-stage detector, in the one-stage detector, it does not have a separate stage for proposal generation or for learning. So it is simply doing the classification of objects in a single step. It is identifying whether it is a background or foreground object. So that is the idea behind this. The examples are YOLO and SSD. So based on this, we have done some work on medical image data. So we have tried with the coronal polyp detection. So coronal polyp means this is the example of coronal polyp on the colon of human body. So this is the polyp. This is the initial stage of the cancer. So we call it as polyp. So once it is find out in the initial stage, we need to cure it. Otherwise, it will go to cancer. So we are going to detect this polyp in the human body, colon. So for that, we have taken a colon image. Here you can see that this is the polyp. And you can see because of the colonoscopy, the image is not having good quality on some of the region. So we use the image enhancement algorithm. So you can see here the quality of the image is improved now. Next, we are going to use a scaled YOLO V4 network. So this is actually a pre-trained network. So we taken this pre-trained network, we added a few fully connected layers, and we trained it using the original image. And this is the original image which contain the polyp, and we have obtained a mask for the ground truth from the doctor. And using this, we have trained the algorithm, and finally we have tested with another image. So this will give you the detected object with the bounding box. So this is the object detection application in the medical imaging. And second, image segmentation. So segmentation means identifying parts of image and understanding what object they are belong to. So segmentation lays the basis for performing object detection and classification. So there are two set of segmentations are available. The first one is semantic segmentation and second one is instant segmentation. In semantic segmentation, it classifies all the pixels of an image into meaningful classes of objects. And these classes are semantically interpretable. Say for example, in semantic segmentation, the same previous object I am taking. So here we can see that three cows are in the picture, right? So each pixel is having the same probability here. That means all are cow. So semantic segmentation will give all the values to single color. Okay, because all are cow. So because we are considering the instances are same. Okay, but in case of instant segmentation, it identifies each instance of object in an image. That means each cow separately, cow 1, cow 2, cow 3. Previously, we have taken all the cows together, but in instant segmentation, we are taking each instance by its own, one by one. So in segmentation, what we do is we will take the convolutional operation followed by batch normalization and ReLU. So this blue representation, green means pooling, and we are doing this operation for a n number of times so that we are getting abstract object information. Then after that we will do upsampling. Here we are doing downsampling by means of pooling. Here we are upsampling by means of interpolation. So we upsample the data. Similarly, we are doing the convolution and batch normalization with ReLU. So this side is known as the encoder, and this is known as the decoder. So we will encode the data first and find out the probability of each object, then we decode it and get into different category. So here you can see this is the input RGB image and this is the segmented output we are getting from the segmentation. So here we have done some work on optic disc segmentation in medical imaging. So here we developed our own methodology. Here you can see that this is the optic disc in a fundus image, and we wanted to get the optic disc to decide whether the person is having glaucoma or not. So for finding that, first we need to detect the optic disc, and then we need to optic cup, and we need to find the optic disc to cup ratio. If it is greater than a specific value, that means the fellow is having glaucoma. If it is less than the threshold value, he is fine or normal. So for that we have used a methodology, and initially we have taken the image from RGB to HSV to get the information, that is illumination information. After that we have done adaptive histogram equalization to improve the quality of the image. Then we done a network, that is an encoding decoding network we have done. It is a customized network. This side is the encoder and this side is the decoder, and we have predicted output like this, and this is the correct ground truth provided by the doctors, and this is the image outlined on the optic disc. So we have used 4 set of data sets, and we have obtained some results in terms of sensitivity, specificity, accuracy, and overlapping ratio. Overlapping ratio is how much amount of overlap is with the ground truth with the predicted value. So here you can see that we are getting an overlapping ratio of 97% and with an accuracy of 97.86 for this data set. And next is CNN is used for medical image classification. So for classification, we can use generally existing pre-trained networks like AlexNet or GoogleNet BGG with the transfer learning with the fine tuning. So here we have done one classification of eye image, generally with a normal image and a dry AMD and wet AMD. AMD is nothing but age-related macular degeneration. It is the problem happens to the human eye whenever we are getting aged above 50. So if you consider a normal image here, you can see that the main person responsible for this AMD is the RP layer. For a normal person, the RP, that is retinal pigment epithelium layer, that will be a normal line like structure. But in case of a dry AMD, this RP layer having some perforation, so we call it as a drasen. And after it is moving from dry to wet, this region will be losing, RP is lost and the fluid will come inside. So this is known as wet AMD. So this is the vision during normal, during dry and wet AMD. So here we have developed a methodology to detect AMD using a multi-scale neural network. So here we have a 3x3 convolution with a few layers, and then we have 1x1, 3x3 and 5x5 layer. So this is known as the multi-scale neural network because we are taking different scales with 1x1, 3x3 and 5x5. So we are selecting the multi-scale network for getting more local features. So we have tried with the different combinations of 1x1, 3x3, 5x5, 1x3, 1x1, 1x1, 3x3, 1x1, 1x5, 3x3, 5x5. And finally, we are getting a better result with these 3 combinations. That's why we chosen this one. Similarly, we have taken different combinations of the other networks, and we are getting good result for the combination of 16, 16, 32, 32. So that's why we have chosen the network structure like this. So in this case, we have taken 90% of data for training and 10% data for validation. For AMD, we have 41,000 data, and normal we have 46,000 data. For validation, we have 4,500 AMD and 5,000 normal data. So in addition to that, we have tested with the AMD 500 and normal 250 and other data sets like 55, 206, 15, 15 and 48 and 50. So when we tested with the AMD data set, only 2 of the images were misclassified, and we are getting an accuracy of 99.73 and an AUC value of 99.99. And after that, we have tried to see how the network is making a decision, because a doctor can simply visualize this image and he can tell it is a normal line, so it is normal. There is some perforations, so it is Drasen, and here it is perforations are having leakage and it is having wet AMD. But how the network is identifying? So for that, we have generated the gradient class activation mapping. So gradient class activation mapping is nothing but we are taking the penultimate layer of the classification layer and placing that it on the original image. So when you place the penultimate layer output on the original image, you can see that there is a yellow plus red color line. So this is known as the RP plus Bruch's membrane. So this is actually a normal line for the normal image. And when you come to the AMD image, you can see that the Bruch's membrane plus RP layer is having some perforations that is clearly visible in the structure. So this is how the CNN identifies that there is a problem in the image. And similarly, when you come here to the wet AMD, you can see that the RP layer and the Bruch's membrane come up to here, and after that you have a gap. That means there is a breakage of the RP layer. So that's why the fluid is coming inside. So this is how the CNN identifies that this is wet AMD. So this gradient class activation map will give you how the CNN identifies different images with different uh, structures. Next is OCT denoising. So we can use image CNN for denoising. So here we can take a OCT image, that is optical coherence tomography image of eye. It will give you the different layers of the eye. So first it is giving the noisy image input to the convolutional neural network. Then we learn the noise. Then we find out the noise from the image, and that will be subtracted so that you are getting the denoised image. So this is uh, the way by which we are using uh, CNN for denoising. And here instead of classification, we are using regression. That is the only difference with the classification. So here we use the final layer as regressor to get the noise information. So here you see this is the input image, and this is the ground truth image, and this is a denoised image. You can see using a neural network we have denoised the image. You can compare this with the original image, and we can find out the values like PSNR or structure similarity, etc. like that. So with this, I finish my session. If you have any questions or queries, you can ask. Thank you.
Sir, thank you so much, sir.
Thank you. Any
So
questions?
this is, the participants, if you are having any queries, you can ask. Okay, sir. Sir, thank you so much, sir. Your session was really very interactive and useful for us, sir.
Thank you.
Thank you so much, sir. Thank you, sir.
So I also would like to thank uh, Mahalingam College for inviting me for a session, and I hope you get some information, because in a small span of time it is quite difficult to give more details. But I thought you get some information from this presentation. Nice to meet you all. Thank you. Have a nice day.
Thank you, sir. Thank you so much, sir. Thank you, sir.
just commercially made grade. If you are going for research means you require a clinical grade equipments. That's available in, okay. So one participant, any one participant? Yeah. Come. Yes. This is the equipment that is, it is Mindwave mobile. For small kind of applications, you can utilize this for your projects, for your verifications, right? But it cannot be implemented for the research purpose because number of channels is very less, right? So using this, you can find, yes, sir. Okay, so can you just introduce yourself?
அனைவருக்கும் வணக்கம். I'm Nandan from third year CSC. இதே காலேஜ் தான் MCET.
So, do you know how complex EEG is? Why it is said to be more complex, EEG? But ECG is very simple. The cost of the device is also very simple, or very small rather. Why EEG is said to be very complex? Any reason? So this is only a laboratory device which is capable of going for only 5 channels. But when you are going to a hospital, they will be putting 18 electrodes on your head. There will be one reference electrode. Normally for acquiring any potential, we need a plus as well as minus. A potential difference we have to take. So one electrode will be taken as a reference and the remaining electrodes will be placed on your head. And moreover, what is the problem with respect to EEG is, you are having your 5 sensory organs, right? So all of you know very well. Whenever, suppose if you are blinking your eye at the time of taking your EEG, I think it will be what? There will be a change in your voltage or change in the duration. Okay? And similarly, suppose there is a pleasant smell is coming, automatically what? Your EEG will be affected. And moreover, if you take an EEG when you are sleeping and if you are not sleeping, I think probably the EEG varies. That is the complexity of your EEG wave. Okay? So through any 5 sensory organs, if there is any change, right? Automatically your brain will detect and automatically accordingly your waveform will change. And moreover, the amplitude is also very, very small. Amplitude in the sense it is nothing but with respect to y-axis. And moreover, the time period is also what? Because the frequency is very, very small. Okay. So all your alpha, beta, all your waves are what? Very, very small frequency. So normally we will be experiencing with respect to high frequency, right? So frequency in the sense the number of cycles per second will be your frequency. That means here we are having a lower frequency, and moreover, whenever if you put any electrode, there may be what? Through the 5 sensory organs, you will be having what? The corresponding changes with respect to your waveform, and moreover, these electrodes may be what? Sensitized to background noise. The noise is also coming into picture. So what thing you have to do is basically, first of all, you have to filter. First of all, you have to filter the noise. You will be getting your signal. The amplitude is also very small. You have to amplify the signal so that you can able to go for any form of analysis. And moreover, this EEG signal is said to be a non-stationary signal. That means time to time, the characteristics changes. It is not a stationary signal like your sine wave. That is the complexity of EEG, but ECG is not a huge issue because you are having a PQRS complex will come. Depends upon the amplitude and depends upon the duration. There may be a problem with respect to your heart. Okay. But which one is very important? Whether heart is very important or brain is very important? Which one doctors are giving more importance? Brain. Why? Recently, I think you can hear news about brain dead, so the organs are donated, right? Once the brain is dead, almost all your organs will be coming to your close. It will not function because it is only sending the signal. Okay, so even now you can able to imagine that how God has created us actually, right? We are having electric potential, but normally we know that your battery is creating or some other device is producing a potential. Our body is also producing potential that we are recording by means of what? Electrodes, either in the term of what? ECG, or in terms of EEG, or in terms of EMG. Okay, so when you do an analysis with respect to these type of signals, okay, this is called your biosignal analysis. Okay, this is called biosignal analysis. This you can do for one dimension, right? So 2 dimension also you can do. That is basically with respect to your CT, MRI, ultrasound. Okay, nowadays PET is available, SPECT is available. Okay, but whenever the term changes, PET, SPECT, etc., the cost of the machine is also increasing, right? That means what? You can able to go for a closed scan of the particular organ. Okay, and moreover, my advice for the researchers, particularly, whenever if you are doing anything with respect to biomedical imaging or biosignal analysis, try to vet it through a doctor. Okay, even though you are doing clinical analysis you cannot do. As an engineer, we can do what? We can able to characterize the particular signal, but unless otherwise, if it is not vetted by a doctor, your research will go as a waste. Okay. Nowadays, people are doing ultrasound based analysis, meaning ultrasound can be used for analyzing your kidney, or you can use it for your lungs. Lungs, you know, when the lungs are functioning properly, as well as liver also you can do, and lungs also you can do. You don't imagine that there are more than 15 to 20 types of defects are happening through the lungs. Recently, COVID is one. Likewise, there are multiple things are there. So, which one is very simple, which will not cause any problem to the patient? Which one? Ultrasound or CT, MRI? Which one? Any idea? Now, earlier, I worked with medical image analysis only. I did with respect to ultrasound, right? So, some of my scholars, they have completed using ultrasound, right? Which one is very simple, which will not cause any problem to the patient? Which one? CT, MRI, PET, SPECT, mammogram, which one? Ultrasound is very simple, right? Okay. So, you know about ultrasonic waves. Normally, we cannot hear that. It is beyond 20 kilohertz. Normally, human beings cannot hear that ultrasound, right? So now what we are doing is we will be sending ultrasonic waves through a probe to your body. What your body will do, it will absorb something, it will be reflecting something is back. That will be collected and it will be recorded in a sheet, which is called as what? Ultrasound waveform. Normally, whenever fetus, right? Suppose they want to identify the fetus, they want to know the stage of the particular fetus. Normally, they will not go for CT or MRI because for fetus, what? The ultrasound is not harmful. So, anything we want to go for a fundamental research, particularly with respect to kidney or with respect to lung or with respect to liver, try to go for ultrasound based image or ultrasound image. But when you are going for analysis as far as an image processing engineer or computer vision engineer, normally your ultrasound image will be like only black and white. Only black and white. Whether there is a disease is available or whether the disease is not available, whether it is the problem with respect to noise, nobody knows. But doctors, they are going for clinical analysis. What is clinical analysis? They will be going for the complete blood test. Blood test automatically or WBC will say the things, right? RBC will not say anything, but WBC, normally there is a range is available. Okay, if it is, it will exceed actually. It will exceed. That will exceed in terms of geometric way. You will be getting 3 lakhs or 10 lakhs or 20 lakhs. That means what? The person is having a problem. This is called clinical analysis. That is why what I'm telling is, whenever if you are going to do your research, particularly in biosignal analysis or biomedical image analysis, try to vet it through a doctor. Which doctor? Normally, doctor will not do anything. There is a person called a radiologist. Radiologist is also a doctor. Okay, try to get a second opinion about from the radiologist. So whenever if you are doing a research and finally if you are submitting your thesis, attach that report also. That will give more validation for your particular research, right? Okay, is it clear? So biomedical, now it is growing. Now it is growing. For your information, Ganga Hospital is available in Coimbatore. How many of you knows? I think all of you know. But there is a research center available at Ganga. Probably if you want to do your research for taking your signals or images from Ganga Hospital, suppose if you have to write a consent, right? So your mutual agreement will be there. So when you write, automatically what? They will give their images, okay, based upon the condition that they will not reveal the patient's name. That is a condition. Because it is a subject, they will not reveal the name, they will give the images. You can use it for your research. And whenever if you are doing a publication, it will be a joint publication from Ganga Hospital with respect to the individual. That is the only condition. If you want, you can contact Ganga Hospital whenever if you are doing a biomedical research, right? And nowadays, there are hospitals, even Ganga Hospital is also providing fundus images. But even though it is not closely, they are doing only with respect to bones. They are going to deal only with respect to bones. Ganga Hospital is meant for that. Even then, the small sort of fundus images they are collecting and they can able to give. And even nowadays, even though through your teeth also people are doing research. Right? Any dentist you can contact, you can get the image and you can able to identify what is the problem with respect to the teeth. Is there any disease? Even teeth cancer is also now available. Okay. That is normally we call it as carcinoma. So that is also happening. This is not only, cancer is not happening only in terms of what? Not only in the skin, not only in the part, it is happening everywhere. Okay. That abnormality, I think probably you can able to detect. Okay. So this is a small piece of what, as far as people are want to do their research, particularly in terms of biosignal or biomedical analysis. But India, very small, even NITs or IITs are doing, right? Dr. Mahalingam, I think major research will be on biomedical. But even yesterday also, I think the professor has gone for 3D, right? So very small part of research is happening at different NITs and IITs, right? But as far as college level, it is slowly picking up. It is slowly picking up. But it is a nice decision if you want to do your research, particularly in image, biomedical analysis. But conventional image analysis is very simple, right? So no need of the problem, but acquiring an image is not an issue. Because now, because of your mobile phones, because all the images are digital, anytime you can capture an image, anytime you can delete an image. Now image becomes what? It is not costly. Earlier days it is costly. Because if you want to go for Fuji, right? You have to buy the film, expose the film, take the photo. Nowadays it is not the case. Okay. It is very simple. Anytime you can take your image, you can process the image. Okay. If you are going for a little bit of fundamental case, you can go for simple image processing will do. But when you want to go for analyzing your image, definitely image processing, partly helpful, but it is not fully helpful for you. You have to go for vision-based analysis or image visualization as well as image analysis. Is it clear? Have you captured that? But Mr. Safiq is doing his research under my guidance. He has started his research. His area may be like emotional detection from EEG signals, right? Even we can able to, we are going for in the direction that, suppose if you are sleepy, because your EEG signal is getting affected by every 5 sensory organs, right? This can be helpful in terms of what, whenever a driver is closing his eyes, that can be detected. Or suppose in the classroom also, if you are started going for a sleep, that can be identified earlier, and we can go for analysis. So not only for sleeping, but other mood also, right? We are happy, or if you are sad, other conditions also, right? That is his research. He has started, and normally for these types of things, some repository signals are already available. But unfortunately, certain modalities we don't have, right? EMG, we don't have any reference, right? Any reference material is available. But EEG reference materials are available. For ECG also reference materials are available. But unfortunately for EMG or certain modalities, we don't have any reference, right? So that means what? In repository, we don't find any signals, right? Now this is also an area of research. If you are acquiring that with the help of the hospital or under your name, you can also create a database. There are multiple databases are available. And moreover, if you compare India with respect to China, the number of research papers which is coming from China is tremendous. It is geometric. Every day it will be like multiples of hundreds. Okay, even you can find the papers very small. Even college level students, they are publishing their research. But that is not happening in India. Whenever, if you are going for research only, people are doing. But very small amounts are happening at IITs or NITs, but very large number is not happening. But in China, I think very tremendous number of papers are coming day by day. If you accumulate it for an year, that will be going close to more than 50,000 or 60,000 papers. All the papers are good quality of papers, but it is not happening because of obvious reasons. We are not getting pressurized, but there is a pressure. They are giving full financial support. That is why the number of papers which is coming from China, and many quality research is also happening. Okay. This is for your youngsters. I think now also you can take up. Okay. And each and every semester try to go for a little bit of acquiring some sort of research theme and try to convert that into a project, even though it is a mini project, and finally you can convert that into a big project. Okay. But it is happening at some of the leading institutions, right? The PSG, TCE, there are small researches are going, because in every department there are some research groups. Through the research groups they are promoting actually. So good morning. So I'm officially coming back for taking over this session. So this is my research almost like more than 20 plus years back, right? This not happened here previous year or 2 years before. It happened almost like 20 years back. But even then, the first day, Dr. Mahalingam, I think, has indicated something about wavelet transform analysis, right? I think probably if you are very clear, I think if you have attended his session, he is very much focused with respect to signal processing alone. But even though there are machine learning has come, our CNN has come, but he is very much focused only with respect to signal processing, because once if you are good at signal processing, probably what CNN and ANN will be very simple, right? That is his philosophy. And earlier, before going for IIT Palakkad, he was working for Amirda earlier, right? So he was working for Amirda. He is my very close friend. He was working for Amirda. After that, he went to Samsung. In Samsung, he has got multiple patents for some of his ideas. Basically, he worked with Samsung in terms of signal processing area only. And after that, he went to IIT Bhubaneswar. It is in Odisha. I think he was serving there for IIT Bhubaneswar. After that, because the recently constructed IIT Palakkad, he got a transfer, and now currently he is working for IIT Palakkad. That is his history. And here, even though we are very familiar about other transforms, I think ECNs may know, I think probably you are very familiar with respect to Fourier transform. Okay. Maybe like for signal analysis, we will be going for Fourier transform. But I indicated earlier, suppose if you are going for all your biosignals are non-stationary in nature, right? Non-stationary in the sense, the frequency content of the signal which will be varying from time to time. But when you talk about a sine wave, the frequency remains same, right? So when I'm speaking, my speech signal, right, that is also non-stationary, right? Because the pitch varies, okay, and the amplitude varies, okay, everything varies time to time. But when you are conventionally, if you are generating a signal in your laboratory, all your laboratory waveforms are stationary. But all your real-time situations, whether it is a biosignal or natural signal, will be what? Non-stationary. Whether I can able to go for any analysis with respect to Fourier transform or a non-stationary signal is a question mark. There is a need or an advent of what? The new set of transform, which is called wavelet transform. So earlier this was introduced from a mathematics professor, right? It is not from engineer. Almost all your analysis was already done by means of mathematics. But what we are doing is, our research is not a fundamental research. Our research is always an applied research. You know about what you mean by fundamental research, right? What is fundamental research? Any idea? What is called fundamental research? What do you mean by applied research? Where we can do fundamental research? Where you can do applied research? Okay. It is partially correct, but you know about the STEM, science, maths, these are all the fundamental subjects, right? For acquiring an engineering, we need some fundamentals in terms of maths, in terms of physics, in terms of chemistry, in terms of biology also. Unless otherwise, if your biology is not clear, we are not clear with respect to ANN. Okay. So what brain is doing, we are simulating that with respect to artificial neural network, right? Natural neural network is God has created. Okay. But the potential varies from individual to individual, depends upon how effectively you are using your brain. But anyway, we are creating that artificially. That is what we are good at biology. I think probably you are good at what? ANN, etc. When you do some research with respect to these areas like physics or chemistry, or these are all called fundamental research. when you want to make for applied research in the sense, already something is existing. If you want to make a small change, right, that is called, it is called applied. I can borrow some concepts from some engineering field that I can able to apply for my condition, and the research becomes applied research. But anyway, fortunately, other countries, maybe with respect to other continents, Europe, US, even then they are doing multiple number of researches are happening only in fundamental. I think there is a famous prize called Nobel Prize, right? Nobel Prize is not meant for engineering. How many of you know? Nobel Prize is not meant for engineering. Nobel Prize is meant for physics, Nobel Prize is meant for chemistry, Nobel Prize is meant for medicine, okay. Other areas maybe literature, peace, other things are what? Directly given based upon the nominations. But it is not meant for engineering. That means what? All engineering ideas what we are doing is meant for what? Not fundamental, it will only applied research. Normally Nobel Prize will not be given for an applied research. That you can apply it for a patent, you can able to get a patent, right? Some royalty will be coming to you based upon the patent. So all fundamental research, that is what I said earlier, physics, chemistry, biology, medicine, etc. These are all the fundamental case. Only the fundamental research only they have given us a Nobel Prize. Okay. Now let us come to this portion. So transform and its need. You are very familiar with Fourier. Okay. Stationary and non-stationary signal. Short time Fourier transform. Wavelets. There are two classifications, continuous, discrete, and finally we are going for applications, right? What is this? Let us not worry about the words, right? What is this waveform? I think probably you have seen in your physics laboratory in your +2 or first year. You know about tuning fork. When you tap your tuning fork, what it will do? It will generate a waveform. But waveform is always what in nature? It is sinusoidal in nature. Normally we call it as a sinusoidal signal. But a sine wave is different, sinusoidal signal is different, right? What is the difference between a wave and a signal? You are having mobile phones, right? Everyone is having a mobile phone. Okay. It is working under what principle? It is under a principle of signal or wave? Signal or wave? Signal. People are now calling it as EM waves. Nobody is calling it as EM signal. What is the difference between a wave and signal? When the signal is traveling in a direction, it becomes a wave. When the signal is not traveling, it is as if like a signal. When you are generating anything in the laboratory, it is not a wave, it is a signal. When you want to use that signal for a commercial purpose, maybe for what? Communication purpose, automatically that becomes what? That becomes what? It becomes a wave. That is very simple, right? So what you are generating in the laboratory is basically what? A signal. Commercial purpose, you are using that signal for some application, it becomes a wave. Okay. Now this is called as what? A sinusoidal signal. You know about this fundamental time period, you can reverse the period, you can able to get the frequency. And when you are talking about a term called as frequency, frequency is given by a person called Hertz, H-E-R-T-Z. That is why under his name only we are calling it as Hertz. Hertz is a unit for frequency. In the earlier days it is called cycles per second. Cycles per second is an old unit actually, right? After Hertz only, he has introduced something called as what? To glorify Hertz, they have given what? Hertz. H is Z. They will be putting capital H followed by small z. So when you are knowing for some of the technologies also, please go through what? Certain history, right? History is also equally important. It is not meant for writing stories, but what is the underlying case also you have to what? Understand, right? So Hertz is a person who has given some what? Weightage for a signal under his name only 5000 Hertz or 5 kilohertz. Now people are going for higher frequencies. People are going for gigahertz. All your commercial applications are with respect to gigahertz, your DTH. Okay, and beyond. Now people are going for what? Terahertz. Okay. The frequency is keeping on changing. Why? Why we are going for higher frequencies? And wavelength is less. Okay. Because your frequency and wavelength is inversely proportional. Because it has come to a formula called C is equal to F lambda. C is called the velocity of light. The velocity of light is always 3 into 10 to the power of 8 meters per second. Okay. And you know the frequency, C by F becomes lambda. Automatically F is going to the denominator. When F is high, lambda will be what? Small, vice versa. Okay. So that is why very popular. That means what? Nowadays you are carrying your mobile phone. Whether your mobile phone is having antenna, without antenna how can you receive? Your mobile phone is also having an antenna that is called as a patch antenna. Antenna is there, unless otherwise antenna is not there, you cannot receive any signal. So when your mobile phone, you are having your RF signal is also coming, RF processing is happening, and you are having other related devices, right? That is why the wave which is coming into your mobile phone is basically what? Microwave. The range will be what? In terms of giga, or 10 to the power of 6 or 10 to the power of 9 megahertz or gigahertz. That is why it is prone to what? Radiations. So that is why normally what we are advising, which power is dangerous, microwave power or electrical power? Both the powers are dangerous. Electrical power, if you want to carry electricity for a different place, they are laying towers, metal towers. That is, they are carrying electrical energy. So for communication purpose, they are erecting an what? Tower, there an antenna is fitted. This is also radiating, that fellow is also carrying actually. The dangerous part is what? Our communication antenna rather than an electrical device. But equally both are dangerous. But that is less dangerous, but here it is what? More dangerous, because we are using only microwaves for our ovens. That will convert that into what? The signal will be converted to heat. If your body is keep on exposed with respect to microwave, automatically depends upon your body condition, that may induce something, mutation starts, that may be converted into what? Cancer. That is why don't keep your mobile phone for very long time, okay, for communicating between one person to another person. Okay, so microwave is more dangerous than electrical energy, right? So let us come to the point. Now this is your sine wave, right? Now first cycle also it is suppose I am determining some frequency is 10 Hz. First cycle also 10 Hz, second cycle 10 Hz, third cycle 10 Hz. Last cycle that is also 10 Hz. That means what? The 10 Hz is a term or a frequency is not changing with respect to time. So this type of signal, what we call it as is basically what? Stationary signal. But we are very happy we are living with respect to what? Handling with respect to stationary signals. What is unfortunate? All your real-time signals are always non-stationary. Okay. How to handle that non-stationary signal is our objective. So transforms, right? Let me not go into detail. Okay. So what is a transform? It is a mathematical function, right? Like a bus moving from one place to another place. So we are having two domains. One is called a time domain, another one is called a frequency domain. Maybe Pollachi, Coimbatore, we can take. A transporting device may be your bus. A transform is basically a transporting device, which will take you from Pollachi, land with respect to what? Coimbatore. Once again, a reverse bus will be there, Coimbatore to Pollachi. In the same way, from time domain, using a transform, I can land up with respect to frequency domain. From frequency domain, I can come back into what? Time domain back. Maybe you can call it as a forward transform or inverse transform. Okay, as simple as, let me not go into what? Detailed discussions, right? But transforms are always doing compression. Transforms are always doing compression. Somebody is interested to do with respect to research on image compression or video compression or data compression. Try to take some of the transforms. There are some popular transforms are available, but anyway, for all the transforms, the fundamental transform is Fourier. Because Fourier transform is given from a person's name called as what? John Baptiste Fourier, we call it as J.B. Fourier. So Fourier is a person's name. Almost all your terms are only coming from a scientist's name. Hertz is a scientist. Fourier is a scientist. right? All forms you are having what? The terms related only with respect to what? From a scientist name only, right? So this is the person. This is a person. Now you please look at the year. 1768 to what? 1830. Okay. What is a century? 1830 means it is 19th century, right? Now currently what century we are now? Yeah. Still the person is getting remembered. Right? That is why research is powerful. Research is more powerful, right? So this is the term he has given, right? So time to frequency, frequency to time. So let me not go into the details actually. The thing is called what? Jean Baptiste Fourier or Joseph Fourier. We call it as JB Fourier or simply Fourier, right? Let me not look into the other names or other initials, right? Let me not expand that initial. But the simple idea will be, for any periodic signal can be expressed using what? Sines and cosines. That is the only term, that is his research. Any periodic function or a periodic signal, I can able to express using sines and cosines. Sine you know, sinusoidal signal. Cosine you know, cosinusoidal signal. Both the fellows are related. That means what? Both the fellows are related with respect to an angle of what? 90 degrees. Or both the waveforms are orthogonal. Okay. That means what? Sine wave and a cos wave is what? Leading or lagging by means of 90 degrees. Or in terms of radians, pi by 2. So 90 degrees is always called perpendicular or orthogonal. So sine wave and cosine waves are what? Orthogonal. That means any periodic signal I can able to represent using what? Two orthogonal signals. That is his research. He has got what? Research and also what? He's got his PhD also through this simple term. This is the only one word of his research. Even after centuries to centuries, we are following the same principles of what? Whenever a periodic signal is available, I can able to express using what? Two orthogonal signal, one may be sine, another one may be cosine. Okay. Obviously, e power j omega t, I can able to express as cos and sine. This is what I told earlier. We can able to express using cos, you can able to express using sine. This is forward and this is your inverse transform. And moreover, so what we are doing, okay, in Fourier, what we are doing means I will be having x of t, that is my signal to be analyzed. I will be having a set of filters, right? I will be having a set of filters. Each filter is having its own cutoff frequency, right? Each filter is having own cutoff frequency. It is more or less like what? The filter commercially what we can call. I think all of you are knowing your filter coffee. Okay. How the filter coffee is prepared? How the filter coffee is prepared? Ladies are here. Huh? You are having a filter, you will put a coffee powder and then water, right? Automatically what? The liquid is coming out, the remaining solid portion is settled at the top. That is the purpose of the filter. Okay. And when we talk about a filter, the hole in the filter matters, right? You can have a small hole or you can have a large hole. You can have finest hole, you can have what? Coarsest hole. Depends upon that the amount of component will be coming out. Similarly, I will be having a bank of filters. The dimension of each filter is not same, right? The dimension of one filter is different, second filter is different, third filter is different. How many filters are there? Infinite filters. Suppose in your signal, I don't know anything about the signal. Suppose in your signal, this omega naught is available, automatically what is output? I will be having an output. If the particular frequency is not available, what is output? It is 0. So this is called as what? One thing is made into multiple, we call it as decomposition or analysis. Okay, this is called signal decomposition. Whether you are going for your commercial signal decomposition or biomedical decomposition, in a transform, what you are doing is obviously what? We are going to decompose the signal. Okay, I can give a simple parallel example, okay, for you so that you can able to understand. You know about a laddu, right? Available in your shop, or you can take about your Tirupati laddu, right? Okay. Laddu is in a good shape. Yes or no? I am not breaking that. Laddu is in a good shape. I think probably everybody will be fond of sweets, right? Rather than the other item. Suppose let us imagine that I am giving a laddu to each and every individual, right? I am giving a laddu to each and every individual. That is my x of t. Okay, I am going to correlate each and everything. My x of t is nothing but your laddu, that is I am giving it to each and every individual. What is the objective is, try to crush the laddu into pieces. You know what is the objective? Try to crush the laddu into pieces. I will be giving a paper to you, each and every individual. You have to write how many bundis are available. You can write 5 or 10 or 100. Try to write how many candies are available. Candy means what? The kalkandu, right? So how many candies are available? You can able to write. Right. How many cashew nuts are available? You can able to write. How many grapes are available? Can able to write. And finally, one volunteer will collect, or a volunteer will ask you, okay, in your laddu, how many bundis are available? What will you tell? 100. How many candies are available? 10. How many cashews are available? Sir, 2. Second person, what you will tell? Sir, my laddu will be what? Same size is same, 100. But unfortunately, I don't have any cashews. But I am having what? Little bit of candy. That means what? The answer is not same. Correct? That means, so what we are doing, even though the laddu is in a good shape, spherical shape, I am going to analyze each and every component present in the laddu. What is the component? What are all the components? Cashew is one component, grape is another component, maybe what? The other constituents, right? Bundi may be another component, right? But we are not looking into what? The substance of sugar. Why we are not analyzing the substance of sugar? Why? Because it is a homogeneous mixture. It is not heterogeneous. Heterogeneous I can able to separate. Homogeneous I cannot separate. When you put a sugar in your coffee, I think can you able to separate once again sugar? Not, it is not possible because it is homogeneous. What is heterogeneous? After mixing, you can able to separate. That is called heterogeneous. Nowadays, people are calling it as heterogeneous group. What is the meaning? I can able to separate. Homogeneous group, you cannot separate. Okay. Always, we are not looking into the sugar substance, right? So what I am telling is, when the laddu is crushed into pieces, what you are doing? Analysis. When you go for analysis, you are telling your answer, 100 bundis are available. That may be one output. 5 candies are available. That is the second output. If no candies are available, what is the output? 0. Okay. Bundi is a major constituent. There will be a number. But a cashew nut as well as candy or the other substance may be there, may not be there. If it is available, maybe I can able to term in terms of what? Some quantity. Maybe 2 in number, 3 in number, 10 in number, 15 in number. Okay. That differs from individual to individual. That means what? One signal is decomposed into what? Multiple pieces. Now I am coming to the reverse. Okay, sir, job is over. Don't eat that laddu. Okay. Try to convert that back into original. So what you will do? You will ask for a gum or something like that. You can convert it back. What is that? This is called a synthesis. Reverse. Okay. So when analysis means a larger component is broken into pieces, you are going to analyze. What is synthesis? All the components are mixed up together without any loss, and then finally you are getting back. But can I able to get back the original laddu? Definitely it is not possible. That is why it is called what? It is not exactly, even though I have written that it is x of t, but fortunately or unfortunately that will not happen because of what? There may be some deformity will happen actually. In all your transforms this is happening. So there will be an analysis, there will be a synthesis. For doing for analysis there is a transform. For synthesis there will be a reverse transform or inverse transform. Okay. Okay. Now what is this? Let me show some pictures. What is this? There are 3 cosine waves I have shown to you. Okay. One is 5 hertz, another one is 25, another one is 50. Somebody told that what? Frequency and time is inversely proportional, right? When the frequency is more, it is closely spaced. When the frequency is less, I think what? It is spaced, the distance is what? More, right? This is nothing but a simple 3 different waveforms. I know the frequency. What is this? I have taken a spectrum. I have taken a Fourier. Now what is the answer for the first waveform? There is a peak at 5. means it is 5 hertz. Second one, there is a peak at 25. I know the answer, 25 hertz. Third waveform, what is the frequency? 50. There is a peak or impulse at 50 or impulse at 25, impulse at 5. I can able to understand this. The previous waveform is what? Time domain. And this is nothing but what? Frequency domain. This is what I told you earlier. Pollachi to Coimbatore. From here also I can come back. Coimbatore to Pollachi. So this waveform is with respect to frequency domain. Previous waveform is with respect to what? Time domain. I think in the laboratory you have come across some device called as CRO. CRO is capable of producing what waveform? Time or frequency? Time domain waveform. There is something called a spectrum analyzer that will characterize your waveform into what? A frequency domain waveform. Okay. This is as simple as. Now, the question becomes very complex. This is also illustrated by the browser, right? Sabarimala. How many frequencies are here? 3 frequencies. I have clubbed or mixed. This is homogeneous mixer. Now, if I look at the waveform, can you able to tell me how many frequencies are there? Now, this becomes complex. Whenever multiple frequencies are present in your signal, definitely by looking at the waveform, you cannot able to say. More than 100% sure you cannot able to say. Now, which one is handy now? In these circumstances, try to take the Fourier. Now, how many peaks are there? 3 peaks. One peak is at 5, another one is at 25, another one is at 50, which will tell you that what? There are 3 frequency components present in the signal. Now, which one is, will be giving more voting? Frequency domain or time domain? If it is a single waveform, both the domains are same. Whenever multiple frequencies are available, time domain analysis is merely a waste. I have to go for what? Frequency domain analysis, wherein for the combined component, I will be getting the frequencies. Depends upon the number of peaks located, I can able to tell how many frequencies are present. Okay, is it clear? Okay. This is a stationary signal, right? 20 hertz, 80 hertz, 120 hertz. Suppose if I combine all the 3 frequencies together, so what I will get? First waveform 20 hertz. 20 hertz is constant everywhere. First cycle is also 20, second cycle is also 20, third cycle is also 20, last cycle is also 20. 20 is the information which is constant. That is why this signal is called what? Stationary signal. That means the frequency content of the signal is not varying with respect to time. The frequency content is what? Not varying with respect to time is called as a stationary signal. For third signal is also same, last signal is also same. If I mix all the frequencies together, like adding all the thing, I will be getting a waveform like this. Now, which one is handy? I have to take Fourier for this. I will be getting a peak at 20, peak at 80, peak at 120, right? This is what I am having 3 mixtures are available. If I take a Fourier, I will be getting a 3 peaks. This is very simple. But which signal I am now here now? Stationary or non-stationary? Stationary only, right? But what do you mean by a non-stationary signal, right? This is a non-stationary signal. First time frame, I will be getting one frequency. Second time frame, I will be getting second frequency. Third time frame, I will be getting third frequency, right? So frequencies, 3 different frequencies are 3 different time slots. Fortunately, unfortunately, all your real-time signal, whether what I am speaking, my speech signal, all your background noise which is happening outside, all are always non-stationary in nature. The frequency is also changing with respect to time. So that is why these types of signals are called what? Non-stationary signals. Okay. Now, this is 20, 80, 120, but 3 different time slots. First time slot I will be having 20, but second time slot I will be having 80, third time slot I will be getting 120. Can you tell me where we are having this waveform? Commercially. Commercially, where we are having this waveform? I think all of you know about radar. Yes? Yes or no? What is the purpose of a radar? Identify an aircraft and identify what? A satellite. We can able to communicate. Okay. When you want to communicate with the satellite, what they are doing? They will be sending a forward wave. They will be sending a forward wave. automatically what after a certain period it will be reflected back. Okay. So one is called forward, another one is called inverse or reverse. Whether it is coming directly, no, after some delay only it will be coming back. After the delay, from the delay I can able to calculate what is the distance of the object. This is what happening at Doppler, etc. Doppler effect, etc. Right? I can able to locate the object as well as the speed of the object. This is using a Doppler effect. Change in the frequency. Forward frequency is different, inverse frequency may be different because of obviously what? It is traveling in the space. Without any interference where electromagnetic wave can travel. That is what our physics, right? So in your room also you can able to take up your mobile phone, you can have your signal. That is why what? Even though your door is getting closed, your electromagnetic wave will come. It is not what we are assuming is directly it is coming in line. It will be like a propagation will be like this. That is why it will jump. Even a small hole will make, right? Find a path. And the signal energy may be different, but anyway you will be getting a signal here also. Now the government has laid so many number of towers, okay. But how much power every tower is transmitting is different, but anyway you are having your signal. But this is the waveform which is captured from a radar. That means what? The radar, when you are collecting a received signal, time to time the frequency changes because the object is also tending to move, the frequency changes. One time slot will be having one frequency, second time slot will be having second frequency, third time slot will be having another frequency. Likewise, multiple time slots if you have, multiple frequencies will be there. But whether I can able to analyze this signal using Fourier is a question mark. Okay. Now, for your understanding, I am having a signal, I am taking a Fourier. Here also I am having 3 peaks, right? Here also I am having a 3 peaks. But what about the signal? Signal is non-stationary. Now the question is whether the Fourier transform is responding properly? No. For both stationary signal as well as a non-stationary signal, my Fourier transform is what? Yielding the same answer. Correct? Yes or no? Okay. I will come to a simple example with you. Suppose he is setting a question paper. Being a faculty, I can have a privilege. He has taken a question paper. He is asking 2 questions. Okay. Can the 2 questions will have a same answer? But unfortunately, our students are writing in the same way and faculties are also putting the marks. Even though the 2 questions are being asked, you are writing the answer not for the question, what the answer you are writing. Okay. Can the 2 questions will have a common answer? No. Where is the problem? Problem is with respect to the student or problem is with respect to the faculty? Student. So now, the problem is not with respect to what? Whether it is problem with respect to Fourier or with respect to signal. Problem is with respect to, not with respect to signal. We cannot blame the signal. The problem is with respect to Fourier. That means, Fourier is capable of analyzing stationary signal alone, but it cannot identify or cannot distinguish a non-stationary signal. Okay, that is a problem. Problem is with respect to Fourier, not the problem is with respect to signal. Signal can be anything. We cannot blame the signal, right? Can I able to blame a signal which is coming inside the room? No, I won't blame. Can I able to blame any signal which is outside present? No, I won't blame. Signal will be as if it will be present everywhere. Omnipresent, like a God. Okay, everywhere it is available. But we cannot blame the God or we cannot blame the signal. But anyway, how you are detecting makes a difference. So Fourier is what? Completely failing whenever a signal is what? Non-stationary. Okay. To make an advent, we are going for a new transform. Okay. This is your real-time signal, right? All your real-time signal. What is the first signal? ECG. ECG is very simple device, right? They will put an electrode, reference electrode may be there. Based upon LUP and TUP, I think what? It will generate a PQRX complex wave. And this will be what? Repeated, it goes. Whenever there is an amplitude is changing or a time difference is changing, there may be a problem with respect to what? The individual patient. Okay. Whenever, if anybody is having a heart problem, what is the initial test? Initial test is ECG. There are multiple tests are available, treadmill, etc. Okay. That depends upon the doctor and depends upon the patient, I think what? It will go. But what is the simple idea will be what? They will take ECG. But doctor is taking ECG. Now for us, what is that? For engineers, this is a signal. This is a signal, electrocardiogram signal, right? ECG. And what about the second one? EEG, electroencephalograph. Encephalon means it is brain. Okay. This is also what an electric potential is created. It is recorded by electrode. That is what Safik told earlier. In the laboratory, they are having 5 channels, but commercially, we will be having what? They will be putting 18 electrodes. Okay. And from 18 electrodes, they will collect, and finally, they will record. Then they will find the abnormalities with respect to alpha, beta, etc. Suppose a person is having epilepsy or person is having what? Some other problem, automatically they can able to identify using what? In EEG. Okay. They will record it, and finally what? That will be converted into a video also, right? And third one is called what? EMG, electromyography. Your muscle movements, muscle contraction, expansion, that will generate what? An electric potential, that is called EMG. But unfortunately, for this, the reference is very small. But even though doctors are taking, but EMG, very small numbers they are taking. But more number of heart patients are available, more number of what? Neuro problems are happening in the world, more number of ECG reference, more number of EEG reference is available, but EMG reference is very small. That is why doing the research in the particular area is also very small. That is why the reference is also very small. When you do any analysis with respect to these 3 types of signals, it is called what? One-dimensional biosignal analysis or biosignal research. In foreign countries, there is a biosignal research group is also available. In foreign countries, they are in US, even Stanford and many standard universities, they are having a separate group for doing the research on biosignal research group. Multiple papers are coming and multiple devices are also coming, right? When you talk about biomedical analysis or biomedical signal analysis, I need a device, right? I need a device. ECG is a device. Without a device, I cannot do that. EEG is a device. EMG, for taking that, I need a device. The devices are given by whom? Who has designed these devices? By doctors or engineers? Engineers. That is why there is a separate branch called as what? Biomedical engineering. Okay. Suppose there is a problem with respect to machine actually. Doctor has to rectify or the engineer has to rectify? Engineer has to rectify. Doctor cannot rectify. Doctor can rectify with respect to a patient, but he cannot rectify with respect to the machine, right? Both the things are going in an opposite direction, there is a problem, either with respect to the patient or with respect to the machine. Engineer has to attend with respect to the machine and doctor has to attend with respect to what? A patient. But why these things are required? Why these things are required? Can the doctor see the patient and then give any advice? The days have gone. The days have gone. Earlier, things have gone. Nowadays, doctors are not seeing and then what? But sometimes the doctor may give a prescribe a medicine by seeing the patient itself. That is a different story. But anyway, these analyses are very much essential. But what we can do as a part of an engineer, we can help the doctors in terms of what? Analyzing this and then we can predict actually. Nowadays, there are researchers are available, early stage of epilepsy prediction, early stage of tumor prediction. Okay. There are researchers are there. Why? All the persons will not have epilepsy. What is epilepsy is basically? Any idea? I am talking about an epilepsy. Normally epilepsy will happen to a few set of persons. Normally they will give a key, right? Key is not doing anything. But it is, but the old story, whenever there an epilepsy is there, people are giving key and then finally what? The foam will come out. Okay, what is that basically? Tamil, we call it as kaka valipu. There is no relation between kaka, etc. Right? What is that basically? Do you know about a short circuit? Short circuit, or plus and minus terminal. If you connect, what will happen? Or fire or only? The short circuit is happening in the brain. Whether it will happen to all? No. It depends upon the genetic condition and depends upon what? His nervous capability, okay, neuron transmission, etc. Sudden short circuit will happen. that short circuit will happen only for a moment. For a maximum duration will be 2 minutes or 3 minutes. Ever long irukka mudiyadhu. Ever long irundha patient will die. That short circuit automatically what? It will be recorded as a huge amount of electrical potential that will be reflected in the different parts of the body. The changes la varudhu illaya. This is happening because of that electric potential. That will happen only for a short duration. Appo, can we able to predict that epilepsy based upon another? We need a history. Or patient pathi we need a record. First year la what is his record? Second year la what is his record? Periodically we can have a record. Based upon the record, based upon a normal person, based upon a person who is having epilepsy, we'll compare. Then we'll come to a conclusion. In the person, other clinical analysis also required, right? We have to go for other clinical analysis. Then we can able to come to a conclusion, or we can able to go for prediction. After some 10 years or 15 years, the person is prone to go for epilepsy. Even now you are having what? Other problems are also happening. Alzheimer's disease. Okay. Other things are like what? Parkinson's. All things are what? An abnormality which is happening through what? Neuro disorders. Neuro disorders. Okay. So whether we can able to identify that neuro disorders well in advance so that I can able to predict. Okay. That is what the engineers are doing for prediction. But doctors cannot predict. Doctors are instantaneous. Doctors are instantaneous. Suppose a problem happens, they will record, they will have all the waveform and finally coming to a conclusion, right? This is what called as what your all your the answer for analyzing this non-stationary signal will be what? Short time Fourier transform. I'll be quickly moving into this. I'll be having a signal. I will not look at the signal as a whole. I look at the signal using what? Only a small portion or a short period. Every short period I am taking the Fourier transform. That is why it is called what? Short time Fourier transform. The window is fixed. So now you please look at the illustration, you can able to understand, right? What is blue color? What is blue color? My non-stationary signal. I told about a window. This is my window. The red color is a window. This is nothing but what? My output actually. You please watch this animation carefully. Window is shifted. The width is constant. The width of the window is constant. Every time the strip is also moving, right? Try to find out the strip is also moving. Earlier the strip is at the left. This is called what? Three-dimensional picture. I am taking the top view. Okay. This is what called as short-term Fourier transform. The strip tells me at what time frame my frequency is. That is why it is called short-term Fourier transform. Okay. That is for every windowed portion I am taking a transform. This is my top view. There are 3 different frequencies are there. These are all the time step. This is an amplitude. Normally we can able to record time, we can able to record frequency, we can able to record amplitude. What is 3-dimensional picture? There are 3 axes. One axis is nothing but time, another axis is frequency, another axis is amplitude. Okay. So this time step, this is my frequency, this is my amplitude. So I have to measure like this. X-axis, I have to make it as a time. This period, I have to make it as what? Frequency. This is my amplitude, right? So I can able to tell the correct information. My amplitude will be what? Directly I can able to attach like 25 volts. And this will be my time step, 0 to 4 or something like that, 0.5 to 4.5. That will be my time step. And this is the corresponding frequency I can able to tell. This is my frequency information. This is my amplitude information. This is my time information, right? This is your 3-dimensional plot. So this is your simple this is your time and this is your, so 3-dimensional plot I am converting into what? 2-dimensional plot. One is with respect to time, with respect to amplitude, frequency with respect to amplitude, right? So this 3-dimensional can be divided into 2 dimensionals of what? I am putting a window, across the window I can able to capture these 2 informations, right? If this is a other width, I think what? The same set of waveform, the corresponding set of. Question is which type of window I have to use? Whether I have to use this window or a square window, triangular window. That is depends upon your application, right? There is no condition that I have to use this window, right? You can use any window. Now the question is, suppose your signal is a low frequency. I may have a frequency which is high frequency also. Whether my short time Fourier transform will capture both? No. That means for a small low frequency signal, the duration is large, I need a larger width. If it is a high frequency signal, the duration is small, I need a smaller width. So my question is, can the window can be acted as a rubber band? What is rubber band? I can stretch out. But that is not happening in short time Fourier transform. The solution for that one is what? Wavelet transform. And this is my wavelet transform. Is what we are having? My signal is there. I will be having what? This is what he has told that it is called what? Mother wavelet. There are two parameters, B and A. B is nothing but shifting, A is nothing but scaling. By changing the value of A, I can able to what? Make your function as a rubber band. I can shrink or I can able to expand. And how many values are available? A comma B. A is your scaling and B is your shifting. And the small illustration try to watch, same signal. Your scale is also available. I can shift it. The corresponding unit is also, this is your wavelet transform mode. If I have a what? Scale is now, I have widened that scale. Shifting, I am doing shifting. Scaling also changing, shifting also I am changing. Okay. And similarly, next scale, okay, I am going to shift the waveform. This also shifted. Okay. Now, which is under my control? The width of the window is also I am changing. Shifting also I am doing actually. That is not happening at short time Fourier. Still I am widened, right? Widened window. Okay. The small square is nothing but what? W of A comma B. That is your wavelet transform output. Still it is wider. From this, what is the conclusion? For handling your non-stationary signal, I have to go for which transform? Wavelet transform. Short time Fourier transform is intermediate. I have to go for wavelet transform, which will be capable of changing the shape of the window or size of the window as well as shifting. So both shifting is also happening, both frequency thing is also happening. That is why wavelet transform is very, very popular in terms of handling what? Non-stationary signal. And moreover, Fourier means only one function is available, but how many wavelets are available? Infinite number of wavelets are available. That is why wavelet research is very, very popular. So I will be skipping all these things, and this is your scaleogram. This is your decomposition, and finally, wavelet transform can be applied for waveforms also, or these are all the applications, right? So for researchers, try to focus on this. We can able to go for signal denoising. This is first application. Detecting discontinuities or breakdown points. We are having a signal, whenever there is a discontinuity, I can able to isolate, I can able to find out using what? Wavelet transform. Detecting self-similarity. What do you mean by self-similar? Self-similar. How many of you seen cauliflower? How many of you have seen cauliflower? Cauliflower, if I am taking a small portion, it will be like a tree. Another portion, it will be a tree. Third portion, like a tree. Whole cauliflower, same shape. But what is the difference between a small cauliflower and a large cauliflower? Volume or size? Size. Size matters. So if I know a small cauliflower, I can zoom it, I can able to get a huge cauliflower. This is called self-similarity in the object. That can be identified by means of what? Compressing images, identifying pure frequencies, we can apply for seismic as well as geophysical. What is seismic and what do you mean by geophysical? What is called a seismic signal and what do you mean by geophysical signal? Seismic means nothing but an earthquake. It is a sudden, measured in Richter scale. If it is 7 or 6, it will be dangerous. Okay, but a small amount, it is not a problem. The sudden signal can be what? Analyzed well in advance. What is geophysical? Where is geophysical is coming? People are going for oil exploration, particularly in what? Arab countries. They are digging a well. What is the depth? Depth will be 2,000 feet or 3,000 feet. They are taking out oil. So they want to locate the oil. What they will do? They will send a forward wave. Whenever there is a liquid is available, it will be reflected back. So these types of signal will be called as what? Geophysical signal. We can apply for video compression, right? So these are all some of the applications wherein what? Do this. This is called self-similarity. The wavelet transform output is also what? The patterns are same in the sense what? The objects are very similar. You are compressing your fingerprint compression, because every individual is having its own fingerprint, right? That means what? If I want to store all the individual's fingerprint, it becomes a volume. I can able to compress the image, or I can able to take out the features, right? Normally you are having your fingerprint based attendance. Normally our commercial scanners are taking only what? The full fingerprint. Instead, try to collect only the feature and then go for feature matching and then detect a person. That is called, for this we need a compression. And of course, these are all the cases. Biomedical engineering, all analysis we can do, EEG, ECG, EMG. But fortunately or unfortunately, EMG references are very small, but other references are high. You can do that with respect to wavelet transform. Then what? Source and channel coding for communication engineering. Non-destructive evaluation. What is this? NDT. NDT nanapa. What is NDT? Numerical solution, distance objects, distance I can able to identify. What is NDT? With this we'll close. What is NDT? Non-destructive testing. I think if you ask a civil engineering student, probably you can able to tell. Suppose I'm having a dam. Dam there is a crack is available. Okay? You are having a dam. You are having a crack. The crack maybe initially it becomes very smaller. Day by day it will become sort of widened because of the compression that is happening on the thing. I want to identify the crack. Using this wavelet transform, I can able to identify the graph by taking the image. I can apply wavelet transform. I can detect. Okay. What is non-destructive? For locating this signal, whether I have to do some operation on the way on the bridge, whether it is required, no. When I destruct the bridge, if I do any analysis, it is called what? Destructive testing. I am not going to damage the building, or I am not going to damage your bridge. That type of analysis is called as what? Non-destructive testing. Even IIT Chennai, they are doing this. IIT Chennai is doing non-destructive testing, particularly in what? Recent Mullai Periyar Dam. They did this analysis, NDT. But even almost in the entire country, they are doing NDT. Without destroying the structure, if you want to analyze, you can go for NDT. Okay. It has been struck up, right? Anyway, thank you, right? Any doubts or clarifications required? But anyway, it is an advanced level of research, but anyway, for I want to make it as more simpler. I want to make it as, these are all the type of wavelets, right? Infinity, that is why I am putting so many dots. Infinity wavelets are available, right? You can use any wavelet for your application. Okay. But Fourier transform only one function. But wavelets means what? There are multiple wavelet functions are available. I'm grouping it also, right? If you are good at maths, if you are good at programming, probably you can do that. Right? Some mathematical analysis is required, and also what? Programming ability is also required. You can write Python code also, or you can use FAMS MATLAB, or you can use MathCAD. MathCAD is also another commercial software, but it is also proprietary, but you can try to use Python. Python OpenCV sufficient. So these are all some of the references. Of course, thank you very much for your patient listening. Because other speaker is also waiting.
Thank you, sir, for spending your valuable time with us in instilling the knowledges towards the participants. Thank you.
Hello, good
Hello,
afternoon, sir.
madam. Good afternoon, ma'am. Sorry for the delay, madam. Sorry, madam.
It's okay, sir.
Yes, ma'am. Ma'am, shall we start the session?
Okay, like here 2 pixels, when stride is 2, this green line have come here. Okay, just between the column 2 and column 3, 2 pixels after that. So this is the convolution with stride is equal to 2. Like this also we can perform the convolution operation. Okay. Now, this is just the final example. Let's say we are getting. So what will happen? Let's say input image is given to you. We need to identify to which different category it belongs to, like car, truck, airplane, ship, or horse. Okay. So we know that in CNN, convolution, then pooling operations are used. Okay. Now, after convolution, let's suppose you have got this image, and like you can just say why there are so many images, okay, in one column, why there are so many number of rows. So basically this depends on the number of kernels you have used. It is not always think that only one kernel we are going to use. We can use number of kernels, okay, and that we will see in the architectures, that how many number of kernels they have used. Basically those kernels are known as the weight matrix, where the weight of the complete model is weight of each and every layer is used to store. Okay, on the basis of those weights you are getting your results. Okay, finally there is also, just see, after convolution there is the ReLU. So basically this is the rectifier linear unit, and you can also call it as the activation function. Like in normal machine learning you may have studied sigmoid function, okay, 10x function, etc. So basically, but in classification in here, CNN model, these ReLU have given better results as compared to those sigmoid and 10H functions. So this is how your ReLU function look alike. Okay. So this is just the graph of ReLU function, that is the activation function. So what will happen here? Just see convolution, you are getting some grayscale image. Okay. And it may be possible that all the information present in that convolution layer is not required. So how to remove those information? So this rectifier linear unit is used to remove extra information which is not required. That is why you can just see in the column 2 very less information is there. Okay. So basically it is written as Gz is equal to maximum of Z, maximum of 0 and Z. Whether the, if value is positive then keep it, if value is negative then it is no need. Okay, then just make it as a 0. Otherwise leave it, and whatever pixel value is there, then that same pixel value will be retained. Okay, now after this, let's come to the first architecture, that is the Linet 5. Okay, I don't know many of you have heard about it or not. So it is the first architecture which have used the convolutional neural network. And just see when it was developed. Just see, it was developed in 1998. Okay, and now today, what is it? Is 2023. Okay. So it was developed by Ian LeCun at the some Bell laboratory where they were working. Okay, so this is just the first architecture which have replaced the manual task of feature extraction. Okay, but and they have also used that convolution pooling layer and etc, back propagation algorithm, so that weights can be optimized. So but what happened in that case during 1998, in that time they don't have big machines. Big machines, I mean to say that the graphics card which we used to use nowadays, that is the GPUs. At those times they don't have that highly configured GPUs which we have nowadays. Okay, so that's why they are not able to use these models for the task. Okay, so they have only worked for the small data, and that data is just for the alphabets and the numbers. Okay, just see here how many convolution they have. Just two convolution layers are there, And then this sampling is the where like nowadays we are using the RELU, okay, like cooling and all those things. So now at that time they have used this, and with the full connections also, fully connected layer also they have used. Okay. Now let's say here input image is of size 32 cross 32. So how it is coming as 28 cross 28. Okay. So what they have done in their architecture, they have taken the filter as a size of 5. Filter size means the kernel has 5 cross 5. So if you are having the kernel as 5 cross 5, so obviously size of that image will be reduced somehow. So what it will be, the formula is just given like here, 32 minus 5, 1 is the bias factor. Okay. So finally it will come out to be 28 cross 28. And just see, 6 is a given number here. 6 indicates that 6 number of kernels have been used. Okay. So let's say at one round it will go up to here output layer. So it will check whether the loss is more loss is there or not. So if loss is more, so what it will do, it will again perform the backtracking task and try to optimize all the weights. Okay. So like that this used to happen. Now this is just the same, like how many, if someone say that what is the size of our network, so we always say size of a network in terms of parameters. Okay, that how many parameters it is going to learn. So how many parameters it is going to learn, it depends on the kernel, that is the weight matrix. So weight matrix, if your weight matrix is of size 5 cross 5, then it will be the 5 cross 5 plus 1, okay, and into 6. 6 means 6 number of weight matrix we are having. So total 156 parameters. And connections also you can make it as if there is 28 cross 28, so it will be mapped with this. So these are just the number of connections and number of fully connected parameters also you will get via the multiplication of them. Okay? Just the image size and the final feature map size. Just see, this is just the code of this LeNet. So whenever you have to write your own code also, what we have to always start, see, these LeNet model based on the sequential architecture. Okay. So in sequential architecture, we have to write, this is just a code present in the Keras. In Keras, we have to install the Keras libraries. Okay, so model is equal to Keras.sequential. Okay, we are starting with it. Now we have to add all the layers. So we know that what layers we are having. The first one is the convolution layer. Okay. So first convolution layer is there. Model.add layers.con 2D filter. How many filters? 6 filters are there. And filter size is of 5 cross 5. And activation, at that time they have used the sigmoid, but here I have just written as RELU, which nowadays we are using. Okay. Even there are different version of this RELU also. So RELU is mentioned here, and what is the input image size is 32 cross 32. And grayscale here. Then again one convolution average pooling layer. Then you have to flatten. That is the fully connection layer here, just a flatten. Okay. After this, you have to perform the full connection. Just see here, C5 layer is equal to 120, F6 layer is 84, and finally output is 10. So everything is written like this. So just see here, total number of parameter when we compute, initially it is 156 which I have told, that is 5 cross 5 plus 1 into 6. Okay, so that will come out to be 156, and total in the same way if we are going to do total number of parameters, what they have got is around 60,000. Okay, that is 61,000. So these are less number of parameters. So like that, after this architecture, many people have got motivated, and then they design their own architectures also, but after 1 decade. Okay, 1 decade only after that they started working on it. So this is just the first CNN architecture. Okay, now after this only people started working or thinking in that direction, that without feature extraction how to work on the data. Okay, so that is the LXNet. So LXNet was developed in 2012. So now DNet was developed in 1998. It is developed in 2012. Okay, scale video recognition challenge in 2012, and there they have won that challenge. Okay, by developing their method, so they won that challenge. And how they have trained their models, just see, in that time they have used the GPU, that is the graphics processing unit, for running that code and for training that number of parameters. But in LXNet they have the 60 million parameter, which is very, we can say, which is a very large number as compared to the linet parameter, which is just a 60,000 parameter. So you know, for 60,000 even it is taking lot of time, normal computer. So 60 million means it is not able to work on the normal laptop or a computer. So for that we need to have a graphics processing unit. Okay, so they have just come up with the results where the error rate was just only 15.3%. Okay, and after that next best entry found was just 26.2%. Means it is a huge gap. It means that they were able to achieve very better results as compared to the other normal architectures. Okay, normal machine learning models and on those. So they have just worked on this data set. This data set is named as the ImageNet data set, and so many number of training, validation and test images in it. So basically now just see, this is my we can just say how exactly LXNet architecture look alike. So it contains, just see, 5 convolution layers and 3 max pooling layer and 3 fully connected layers. Okay, so these are more as compared to the linet architecture. Okay, this is how it used to look alike. And they have made image size of different, and number of filters also, filter size was also different, and so on. So now just see, they have taken the input as 227 cross 227, and filter kernel size they have kept as 11 cross 11. Okay. Why I was telling you about a stride, just now look at here. Because from LXNet everyone is now using this stride concept also, that how much we have to shift the kernel while performing the convolution task. So like they have used the stride as 4 and 96 kernels, I mean 96 filters they have used. So if you want to find out what is the value of the, what is the size of the next block or the image which you will get for 96 filters, so it is coming out to be 227 minus 11 divided by the stride size plus 1, so that is the 55. And then again convolution, then again convolution, max pooling, and so fully connected layer, and finally 1000 softmax. Means this is the number of categories in which we have to get the output. Okay, 1000 images we are having, means 1000 categories, not images, 1000 categories we need to classify. Okay, among one image need to be classified among any one of that particular the output side. Okay, this is just one, that how to compute the output volume I have told you. And if someone say what is the number of filter, so filter size is 11 cross 11, and since AlexNet was for developed for RGB images, ImageNet dataset contain RGB images, so it means that your filter should also be of that type. So 11 cross 11 into 3 and into 96 means 96 filters you are going to use. So it is coming out to be 35K. So this is just for one layer. Okay. So like that, if you are going to compute for the other layers also, you will get more number of parameters. But one thing you have to remember, when we have to do the max pooling, uh, in max pooling we are just reducing the size by half. Okay, size is reduced by almost half. So now let's say if we are just reducing the size, do we really need to learn that weight? We don't have to learn anything. It means that number of parameters in that layer is zero. Okay, because we are not learning, so parameters are also zero. Which have used the concept of RELU, that is the rectifier linear unit activation function. They have performed normalization. Okay, concept of that batch size. Okay, so like this here, you have the, just a second. So now here, these are just the number of layers for LXNet, and this is just for the layers which is in the linet. Okay, so these are so many in LXNet. These are so many as compared to linet. Obviously, then in that case it need a very high powerful system in which all these images can be trained. Okay. Now the next architecture in the same category, that is in the sequential architecture, is the VGG net. Sequential, why we are saying? We are performing convolution, then max pooling, then convolution, max pooling, convolution, convolution, like this. So this is a sequence. So that is why these are the model which is present even in the Keras. When you have to design a sequential model, you have to first call that function, that is the Keras dot sequential, that you are going to create a sequential model. So VGG is also in that same category. So basically VGG stands for Visual Geometry Group. Okay, this is just the, if someone asked you what is the full form, it is the Visual Geometry Group, and it was developed by Simoyan and Zizerman in 2015. Okay, and it was published in the paper, that is the Very Deep Convolutional Network for Large Scale Image Recognition. Okay, and they were the runner up in that same competition which held in 2014, in which the Alex and his team participated in 2012, right? So but now the VGG contain 140 million parameters. We know that LeNet contains 60,000 parameters. Our AlexNet contains 60 million parameters. Now VGG is containing 140 million parameters. So it means that network is very large. If network is very large, again the same, we need a powerful machine or a computing device which can compute all those parameters, okay, in a less time. Otherwise it will take so long to train your model. So basically now let's see the architecture of VGG net. Okay. Now this is just the architecture of VGG net. What they have done, they have taken the input image, they perform 3 cross 3 convolution, and 64 is representing the number of filters. Okay, like 3 cross 3 convolution 64. Then 3 cross 3 convolution 64. Right? Means 2 convolution layer followed by 1 pooling layer, which is reducing the size of image by half. Okay, then again 2 convolution layer, then pooling, 3 convolution layer, then pooling, again 3 convolution layer pooling, and so on. Just one thing you have to see here, just difference also, like filters are increasing, like there is 64, again then there comes to be 128, then double of that is 256, again double of that is 512. Okay, so like this, and then last 3 fully connected layers are there. So they have come up with this idea. Now in this idea, the filter size is remain same everywhere. They have not new change in the filter size. Like in the AlexNet there was 11 cross 11 also, and 7 cross, and all those different variant of features are there, filter size is there. So but here they have kept the convolution filter size as same, that is 3 cross 3. Okay, small filter stride is 1, padding is also 1, means if you want to insert some boundary values then you can just insert that, but the padding they have kept as 1, that is called as the padding. If you want to insert some extra row and column at the boundary, means boundary pixels value if you want to create. And max pooling they have performed as 2 cross 2, means reducing the size to half with the stride as 2. Okay, so now we know that AlexNet was 8 layer, but VGG comes with 2 different variants, that is VGG 16 and a VGG 19. So the architecture which is given here is VGG 16. Okay, just look at here how many convolution layers and fully connected layers are there. So that will become as the number of layers in the VGG network. Okay, like that in VGG 19 you will have more number of layers, 3 more convolution layer you can add. Okay, in that case just side will just increase by little bit. So in that competition what have happened, that they have achieved just a 7.3% top error, top 5 error. Okay, just a 7.3%. Okay, so it means that it is better than the AlexNet which was developed, right? So this is just the VGG architecture which look like this. Okay, that is the same image, convolution is there and number of filters are 64. Okay, that there is no reduction in the size, so it will remain 224 cross 224. Now in the next there is the pooling, blue color is the pooling, reducing the size by half. Okay, 11 cross, and then number of filters they have chosen as 128, and same like this. So this is just the final VGG 16 architecture. Okay, so this can be have, or we can say this have been utilized by so many people, and still many people are using it with different variant. Now, as they have said that they have used everywhere 3 cross 3 convolution. Okay, so why they have used that 3 cross 3 convolution? Like in the earlier architecture, they can have the different versions of that filter size. So basically, the concept is that, let's say this is just the given image. Okay, it is a 7 cross 7 image, let's say orange color. So we know that if filter is of 7 cross 7, at least we when we apply that convolution, we will get 1 pixel value in the middle by performing all the averaging and all those things. Okay. Now idea was that in that they have to compute a lot of things. Okay, so many operations have to be done. So what they did, why to work on 7 cross 7? Why not to work on 3 cross 3 but 3 times? Instead of 1 time, just do it 3 times. It will give the same result. So like here also, they have just performed 3 cross 3 on that image. This pixel you will get, middle one of that is this one, and then middle one of this one is this pixel, and middle of this pixel is this. The finally, when you perform 3 cross 3 three times, you will get the same result when you do 7 cross 7. Okay, so this is just the idea they have taken. Okay, they have just removed that because in that case number of parameters are reduced, because if you are taking 7 cross 7, parameters will be more. Okay, you have to optimize more number of weights. So now in this case, they were just second in the classification and first in the localization. Okay, and size, and the model was trained on 4 NVIDIA Titan Black GPU for 2 to 3 weeks. We can just say. So it means that in VGG we are getting better results as compared to LXNet. So we can say keep it simple, even though we will get the good results. Okay. So this is about VGG net. Now, let's say Google Net is also there. Many people used to say it as the inception, okay? That the one model. So, it was just as a name is there, it was developed by Google team under the leadership of Christian CJSD et al. In 2015. So, in the same competition, they have participated where VGG people have participated. Okay, same competition, and this Google Net have won that competition. Okay, he was the first one, and the first who won this. It has 12 times less number of parameter than LXNet. So LXNet we know it was having 60 million parameter, and VGG 16 is having 140 million parameter. So who is better? More number of parameter or less number of parameter? So we say obviously who is having less number of parameter is better, because it is 12 times less than the LXNet. Okay? So, and also giving better accuracy. So what actually the logic they have followed? So they have the model as a 22 layers. Okay, the model look like this. Okay, this is a very big architecture. It is not able to fit here, so I just put it here like in this way. So, but the main thing about this architecture is all the efficient inception module. Okay, so it's straight from journal approach of simply taking convolution and pooling layer on the top of each other. We are just putting over one over the other, stacking of convolution and pooling layer, and they don't contain any fully connected layer as we have seen in the earlier three models. Okay, and it has just 5 million parameters. Okay, 5 millions are very less. So basically what exactly the inception module they have used, we now till now we have seen that at and then get the final result. So what they did is the same way, apply parallel filter operation on the input image. Okay, that is the multiple receptive field size for the convolution. That is the size of the filter is like 1 cross 1, 3 cross 3, 5 cross 5, and max pooling also they have taken. And finally, they have performed the concatenation of all of them. From previous layer, whatever is their input, they perform convolution in different way and also max pooling and finally concatenated them. So this helped them in getting features of different type. Okay, like for 3 cross 3 you will get different type of feature, for 5 cross 5 you will get different kind of features. Okay, so these help in getting the more accurate result. So basically in this case we can just say like 1 cross 1 convolution is there with 128 filters, so it is applied on previous layer, that is 28 cross 256. Okay, so like this, it is there just the output volume size given. Like here for 3 cross 3, it will just be 28 cross 28 cross 192. Okay, like this it will be the output volume size. Now it may be, so someone asked you what is the final, then you just add all the values like 128, 192, 96, 256 and multiply it with 28 cross 28. This is just the concatenation getting this. Now, number of operation, if someone asks how many operation this Google Net is going to take for this number of inception module, like 1 cross 1, how many it will take? Like 28 cross 28 cross 128 and then 1 cross 1 cross 256. 256 here. So like this you will do for all convolution. Pooling does not require any kind of training. Okay. So total number of operation you can compute in this way and it is coming out to be 854 million operations. Okay. So this is very expensive if we are saying that just for one inception module it is this much. So if you have to insert more number of inception module it will be more. So in order to avoid that, what they did, they have replaced that with this one. Okay. Why to consider as direct 3 cross 3 or 5 cross 5 convolution or 3 cross 3 max pooling? Why not to perform just 1 cross 1 and then performing the 3 cross 3? Everywhere, just add 1 cross 1 convolution size. Okay. So what is happening? So in the 1 cross 1, they are reducing the size by reducing the number of convolution operations. Okay, how? Means just see they have reduced 1 cross 1, convolution is 64. From 256, just see in the previous layer you are having 256, it is reduced to 64. So obviously if it is reducing the 64, then 64 to 192, it will be less in number. Okay, so number of operations we can compute in that way. 1 cross 1, 64 will be 28 cross 28 cross 64. Okay, and then multiplied by 1 cross 1, 1 cross 1, 256 and so on. So now here number of operations are less as compared to the previous one where it was around 800. Okay, so like this. So basically we can just say it is not just you don't have to work for a sequential way. You can also design your model in your own way. If you think that algorithm you have developed this fine, then you can design it and you can get even better result than your Google Net as well. Okay. Now there comes the other architecture also, that is the ResNet. So this architecture came again in the same 2015. Okay. So but it contained 152 layers. So 152 means large number of layers. Till now we have seen 16 layer, like 8 layers, 16, 19 layer, then 22 layer. So this is a 152 layer, which is extremely deep. Okay. So this is a very deep neural network, and people used to say every time if we are reducing the size of our network value present in that, so it means that there will be a problem called a vanishing gradient. When you have to come back propagation in that time, it is not able to give the accurate final result or not able to train itself. Okay? Training problem is there in that case. So that is just the main issue in case of deep neural network. If you are doing, you are making more number of deep layers. So, but in ResNet, what they did, they also the winner in the other competition, that is with the error rate of just 3.57%. Okay. So, but in order to avoid that, what they have done, they have got the concept of residual thing. Okay, that is why you have to just work on a sequential way. Why not to, if you are thinking that your results are getting deteriorated after performing max pooling, why not to take the input again from the back side? Okay, so that concept they have bought. So actually that thing is known as the skip connection. Just look at here this diagram. There is the weight layer. You can just say filters are there. So why, if you are thinking that here at this last layer where plus sign is mentioned, connection, if you think that it is giving less final not good weights here, why not to take some data from the previous layer itself? Just add that thing. Now that problem of vanishing gradient can be solved in this case. Okay, so this is just the concept of residual network. Okay, this everywhere they have put this. Just see here, start from bottom. They have the convolution, then convolution, convolution, convolution. Everywhere convolution they are performing. Okay, and they do not have any fully connected layer except the last layer. So what they every time they are doing this is skip connection, taking entry from back and giving it there. Concatenation of back features here. So this is just the concept used in case of residual network. So this is just the full architecture. Every residual block has 3 cross 3 convolution layers. Okay, and they have used the stride as 2. So this is the ResNet architecture. And one thing you can just say here, if you are comparing with the training error and iteration, if you are having 20 layer and a 56 layer network, so in case of deep networks, your training error will be high. Okay, if you are increasing the number of layers, so it may be possible that training layer will be high. So in that case, you cannot say that it is because of overfitting. No, it is not because of overfitting. It is because of training error. So that is just the concept got by them. And ResNet is of different variants like 34, 50, 101, 152 and so on. Okay, like this. And this is just the accuracy comparison of various model and the various different models. Like a new one is coming, obviously they are coming because they are giving more better results as compared to the previous one. And these are just the number of right hand side number of operations required for different models. Okay, and like I said that we have just seen some architectures which is just used for performing classification tasks. Now some say that why not to perform segmentation. So basically segmentation require two things. One is the downsampling and the upsampling. Okay, so in case we need to upsample the image. Like upsampling, I have told in the max, in like there is the max pooling. So max unpooling is there. So they have used the concept of max unpooling, and the from background information also they are taking. That some information is lost, then you take it from the back. That is the skip connection. So this is just the architecture which is used during the segmentation task. Okay, and you can design your own model based on this architecture. Okay, and with this I'm finishing with this, and if you have any query, you please just let me know. Hello.
Thank you, ma'am, for spending your valuable time on your busy schedule with us in instilling knowledges towards our participants. Thank you.
Okay, so can I leave then?
Yes, ma'am.
Okay, thank you.